Hello there, and welcome to the Cosmographer. The honest answer to what came before the Big Bang is that our own best theory of gravity, run backward, stops working entirely at a sliver of time, just 10 to the minus 43 seconds long, and everything interesting lies on the far side of that wall. Tonight, we walk slowly through 14 serious attempts to see past it. We will stand at the singularity that Roger Penrose proved must exist, and then watch him spend his later years arguing it never really did. We will meet Stephen Hawking's universe with no beginning at all, where asking what came before is like asking what lies south of the South Pole. We will follow bubbles budding off an endless inflating sea, universes born inside black holes, and whole worlds colliding across a hidden dimension to light the Big Bang. And we will end at the one question that decides whether any of it is real, whether the beginning left behind a single fossil we could ever hope to find. So get comfortable and settle in. Subscribe if this is your first time here, because by the end of this list, you will understand not only where the universe may have come from, but exactly how far the edge of human knowledge really lies. Now, let's begin. Part 1. The Singularity. We begin at the one place where every road in physics runs out. To ask what came before the Big Bang, we first have to be honest about what the Big Bang actually was, because almost everything you have ever pictured about it is a little wrong. The Big Bang was not an explosion. It was not a bomb going off in the middle of empty space, throwing debris outward into a waiting darkness. There was no waiting darkness, and there was no outside. The Big Bang was the moment when the entire universe we can observe was packed into a state hotter and denser than anything that has existed since, everywhere, all at once. Space itself was hot and dense. There was no room around it for it to expand into, because space was the thing that was expanding. This is the first idea to settle into, slowly, because the whole video rests on it. When we say the universe is expanding, we do not mean that galaxies are flying apart through space like fragments from a blast. We mean that space itself is stretching, carrying the galaxies along with it. The way raisins in a rising loaf of bread drift apart, not because they are moving through the dough, but because the dough between them is growing. Run that, stretching backward in your mind. The galaxies draw closer. The space between them shrinks. Everything grows hotter and denser as it is squeezed into less and less room. Keep going, back and back, 13.8 billion years, and you arrive at a moment when all of it, every galaxy, every atom, the entire observable universe, was compressed into a volume smaller than anything you could hold. Keep going just a little further, and the mathematics does something strange. According to Einstein's theory of general relativity, our best description of gravity and of space and time themselves, the size of the universe does not shrink towards some small but respectable minimum. It shrinks all the way to zero. At that point, the density of matter becomes infinite. The temperature becomes infinite. The curvature of space-time becomes infinite. Every quantity the theory can measure climbs off the top of the scale and refuses to come back down. Physicists have a name for a point like this, where the equations produce infinities and stop making sense. They call it a singularity. And in the standard picture, the Big Bang begins at exactly such a singularity. A moment of infinite density from which all of space and time unfurled. For a long time, no one was quite sure whether to take this singularity seriously. It first appeared in idealized models, universes assumed to be perfectly smooth and perfectly symmetrical, and it was reasonable to hope that the infinity was just an artifact of that neatness. Perhaps in a real, messy, lumpy universe, matter falling inward would not all meet at a single mathematical point. Perhaps it would swirl and miss and bounce, and the infinity would never actually form. That hope held for years. a quiet reassurance that the beginning might not be so violent or so absolute as the equations suggested. That reassurance was taken apart by a young mathematician named Roger Penrose, and the story of how he did it is worth telling slowly, because it is one of the great pieces of reasoning in the history of physics. In 1965, Penrose was thinking not about the universe as a whole, but about collapsing stars. The assumption of the time was that a real star, spinning and irregular, would never collapse to a perfect point. Penrose invented an entirely new way of thinking about the problem, one that did not depend on perfect symmetry at all. He introduced the idea of a trapped surface, a region where gravity has grown so strong that light itself, moving outward with everything it has, is nonetheless dragged inward. And he proved something remarkable. Once a trapped surface forms, a singularity is unavoidable. It does not matter how lumpy or irregular the collapse is. The infinity forms regardless. This was a proof, not a guess, and it changed the character of the question. Within 5 years, Penrose joined forces with a young physicist named Stephen Hawking, and together they turned this same powerful machinery around. Instead of aiming it at a collapsing star, they aimed it at the entire expanding universe, run backward in time. In 1970, they published what is now called the Hawking-Penrose singularity theorem, and its conclusion was stark. An expanding universe like ours, containing the kind of matter we actually observe, traced backward, must reach a singularity. The beginning was not an accident of oversimplified models. Given general relativity and the matter around us, the universe had to have had a beginning where the theory breaks down. Now sit with the strange double meaning of that result, because it is the doorway to everything that follows. On the one hand, Penrose and Hawking had seemingly proven that the Big Bang was real, that the universe had a definite beginning a finite time ago, that there genuinely was a first moment. This was a triumph. On the other hand, and in the very same breath, they had proven that general relativity could not describe that first moment. The theory that predicted the beginning also predicted its own failure at the beginning. It handed us a singularity, and then confessed that a singularity is precisely the place where it has nothing left to say. This is the crucial thing to understand about a singularity, and it is why the rest of this list is even possible. In physics, an infinity is almost never a real feature of the world. It is a warning light. It is the mathematics telling you that you have pushed a theory past the edge of the territory it was built to describe. When your equations start returning infinite density and infinite temperature, the lesson is not that nature actually contains an infinity. The lesson is that you are using the wrong equations. No experiment has ever measured an infinite anything. Infinity is what our description produces when the description has quietly stopped being trustworthy, and we have not yet noticed. So almost no working cosmologist today believes the density of the early universe was truly, literally, infinite. The singularity is treated not as a description of the beginning, but as a signpost, a marker planted at the exact spot where our current physics gives out, and something deeper must take over. And that something deeper has a name, even though we do not yet possess it. It is a theory of quantum gravity, a marriage of Einstein's account of space and time with the quantum mechanics that governs the very small. Every model you are going to hear in the next 3 hours, every bounce and every bubble and every colliding world, is in one way or another an attempt to supply that missing theory, to describe what happens at the wall where general relativity throws up its hands. Consider for a moment just how hot and how strange that wall is. The temperatures we are talking about in the earliest moments we can even begin to model climb past 1 billion degrees, a figure with so many zeros that writing it out serves no purpose except to make the point that every later record in this entire video, every extreme object and violent event, is a story of cooling down from this. The universe has spent 13.8 billion years doing essentially one thing. On the largest scale, it has been cooling, and the singularity sits at the unreachable hot end of that long, slow chill, the point our thermometers and our theories can approach but never touch. There is one more thing to understand, because it corrects the last piece of the wrong picture. The singularity is not a place. You cannot point to it. You could not, even in principle, build a ship and travel to the spot where the Big Bang happened, because there is no such spot. The Big Bang did not happen at a location within space. It happened to all of space. The singularity was not somewhere. It was somewhen. It was the earliest moment, and it was everywhere at once, because at that moment, everywhere was the same place. When you look up at the night sky in any direction, you are looking back toward that moment on every side, because it is not off in some corner of the cosmos. It is in the past of every point you can see. More than half a century after that proof, the world caught up with it. In 2020, Roger Penrose was awarded a share of the Nobel Prize in Physics for the work he had done in 1965, for showing that the formation of a singularity is a robust prediction of Einstein's theory. It is a rare thing, a purely mathematical argument about the structure of space-time being honored decades later as a genuine discovery about the real world. The proof had simply been correct, and the universe, as far as we can tell, had been paying attention. It helps to know where the very idea of a beginning came from, because for most of history, science assumed the universe was eternal and unchanging. The first person to take the expansion seriously as a clue to the past was a Belgian priest and physicist named Georges Lemaitre, who in 1927 worked out from Einstein's own equations that the universe should be expanding, and who proposed a few years later that if you traced that expansion backward, everything would converge on what he called the primeval atom, a single dense original state. Einstein himself initially resisted the idea, reportedly telling Lemaitre that his mathematics was correct, but his physics was abominable. Then, in 1929, the astronomer Edwin Hubble measured that distant galaxies really are receding, and receding faster the farther away they lie, exactly the pattern an expanding universe would produce. The beginning stopped being philosophy and became a consequence of observation. There is a crucial detail hidden in the singularity theorems, and it is the loophole that makes every later model on this list possible. Penrose and Hawking did not prove that a singularity must exist under all circumstances. They proved it must exist, provided that matter obeys a certain reasonable-seeming rule, called an energy condition. Essentially, the assumption that gravity always attracts and never pushes. For ordinary matter, that assumption holds perfectly, but quantum fields can violate it. Under the strange rules of quantum physics, energy can, in small regions and for brief moments, behave in ways that effectively push outward rather than pull in, and that is the crack in the wall. Every model that claims to see past the singularity, every bounce and every creation from nothing, works precisely by exploiting a situation in which that energy condition fails, so that the theorem no longer forces an infinity. The proof did not close the door on a before. It told us exactly which door to look for. This is why physicists treat the singularity with such care, rather than either dismissing it or worshipping it. It is a genuine prediction of a theory that has passed every test ever put to it, from the bending of starlight to the ticking of clocks in orbit to the ripples of merging black holes. General relativity has earned enormous trust, and when a theory that trustworthy points to a beginning, you do not simply wave the beginning away. But the same theory also tells you, with equal clarity, that at that beginning, its own descriptions become meaningless. To hold both of those truths at once, that the beginning is real and that our best theory cannot describe it, is the honest starting posture for everything that follows. So this is where we stand, at the first entry on our list. We have a beginning that our best theory both demands and cannot describe. We have an infinity that is almost certainly not real, but that marks, with great precision, the exact location of our ignorance. The singularity is the confession at the heart of modern cosmology, the place where physics admits that the beginning is a question it is not yet equipped to answer. But a confession is not the same as a full stop. A wall that one theory cannot climb is an invitation to another. And as it happens, we do not even have to travel all the way to the singularity to find the edge of the knowable. There is a second wall, a great deal closer in than time zero, and it is where we go next. Part 2. The Planck Epoch. Let us grant, for the sake of the journey, that the singularity is not real, that some deeper theory smooths it away. Even then, we run into a second wall, and this one sits astonishingly close to the beginning. It is not 13 billion years back. It is not a second after the start, or a millionth of a second. It is a sliver of time so brief that the words we normally use for shortness fail completely. This wall has a name. It is called the Planck Epoch, and it covers the interval from time zero to about 10 to the minus 43 seconds after the beginning. Before that boundary, we do not merely lack the data, we lack the physics. To feel how small that number is, we have to be patient with it, because the human mind slides right off a figure, like 10 to the minus 43 seconds. It is a decimal point, followed by 42 zeros, and then a 1. A fraction of a second, so tiny that comparing it to anything familiar almost breaks the comparison. Here is one way in. Imagine you could take that first sliver of time, that Planck interval, and stretch it out until it lasted a single, ordinary second, one tick of a clock. On that same scale of magnification, one real second, the length of time it takes to say the word now, would stretch out to last far longer than the entire age of the universe as it stands today. That is the gulf we are dealing with. The Planck time is to 1 second roughly, as 1 second is to something much greater than all of cosmic history. Why should there be a special, shortest, meaningful moment at all? The answer comes from combining the deepest constants in physics, and the story behind them is quietly beautiful. Back in 1899, before quantum mechanics existed, before Einstein had published anything, a German physicist named Max Planck was thinking about the fundamental constants of nature. He noticed that 3 of them, the speed of light, the constant that governs the strength of gravity, and the constant that would soon come to define quantum theory and now bears his name, could be combined in a unique way to produce units of length, of time, and of mass. These units owed nothing to human convention. They had nothing to do with meters or seconds or kilograms, nothing to do with the size of the Earth or the length of a day or the mass of a particular lump of metal in a vault in France. They came purely from the structure of physical law. Planck called them natural units, because any civilization anywhere in the universe, having discovered these same 3 constants, would arrive at exactly the same numbers. For most of the 20th century, these natural units were regarded as an elegant curiosity, a mathematical coincidence with no obvious use. That changed as physicists came to understand what a description of the very beginning would actually require. To describe the universe, when it was compressed into the Planck scale, you would need to apply quantum mechanics, the physics of the very small, to gravity itself, to the very fabric of space-time. And we do not have a working, tested theory that does this. Quantum mechanics and general relativity are each spectacularly successful in their own domains, and they refuse to sit at the same table. At the Planck scale, both are essential at once. and their disagreement becomes unavoidable. So the Planck time marks not the edge of what we have observed, but the edge of what we can currently calculate at all. The other Planck numbers set the scene. The Planck length, the smallest distance that is thought to carry any physical meaning, is about 10 to the minus 35 meters. To grasp that, consider that a proton, one of the particles in the nucleus of an atom, is already almost unimaginably small. The Planck length is smaller than a proton by a factor of about 100 billion billion. Below that length, the ordinary idea of distance, of one point being here and another point being over there, may simply cease to apply. And the Planck temperature, the hottest temperature with any accepted meaning, is around 10 to the 32 degrees. Every temperature the universe has ever had since sits below this ceiling. And the whole thermal history of the cosmos is a descent from near this figure. Imagine standing at that boundary, if standing were even possible, and looking toward time zero. The smooth, calm fabric of space you have always trusted, the quiet stage on which stars and planets play out their lives, is not there. As you approach the Planck scale, the fabric begins to seethe. Distances flicker and refuse to hold still. The very geometry of space bubbles and foams, folding and reconnecting so that the notions of here and there lose their edges and blur into one another. Ahead of you, where you expect time to keep running back toward the singularity, the direction called before dissolves. There is no clean earlier to point to, no next frame of the film, because the film itself has come apart into grain. You are not looking at a distant horizon across a great emptiness. You are looking at the last measurable moment of the world, a sliver of the first second, closing off in front of you like a door with nothing legible on the other side. This is not the edge of space. It is the edge of the knowable, and it sits impossibly near the beginning. That churning picture has a name too. The physicist John Wheeler, who had a gift for naming things, called it quantum foam. In this picture, if you could zoom in far enough on empty space, down toward the Planck length, you would find that it is not smooth and featureless at all. It froths. Geometry itself fluctuates, tiny regions curving and uncurving, perhaps even briefly pinching off and rejoining, all governed by the restless uncertainty that rules the quantum world. On the scales we live at, all of this averages out into the placid, dependable space we know. But at the Planck scale, the foam is the reality, and smoothness is the illusion. During this epoch, physicists believe something else was true, something that gives the Planck era a strange unity. The universe was so hot that all four of the fundamental forces of nature, the forces that now feel utterly distinct, were merged into one: gravity, which shapes galaxies; electromagnetism, which binds atoms and carries light; the strong force, which holds atomic nuclei together; and the weak force, which governs certain kinds of radioactive decay. Today, these four behave so differently that it takes real effort to see them as related at all. But in the fierce heat of the Planck epoch, they are thought to have been a single, unified interaction, indistinguishable from one another. Much of the history of the universe afterward is the story of that unity dissolving, of the forces freezing out and going their separate ways as everything cooled, the way a single body of water can freeze into separate, distinct crystals of ice. There is a lovely irony buried in all of this. Max Planck derived his natural units simply because they were beautiful, because they belonged to the universe rather than to us. He had no idea they marked a frontier. He could not have known that the little time he had defined, the smallest tick built from the constants of nature, would turn out to be the exact place where human knowledge stops. He found the units because they were independent of humanity, and only decades later did we learn that they mark the boundary of everything humanity can currently see. To appreciate why quantum gravity is so hard, it helps to see why the two great theories refuse to combine. General relativity describes gravity as the smooth curving of space and time, a continuous, elegant geometry that bends around mass. Quantum mechanics describes the world of the very small as jittery, probabilistic, and granular, full of sudden jumps and irreducible uncertainty. Each theory is fantastically accurate in its own domain. General relativity governs the large and the heavy, galaxies and stars and the orbits of planets. Quantum mechanics governs the small and the light, atoms and particles, and light itself. For almost every situation in the universe, only one of the two matters, and physicists can use one and ignore the other. But the Planck epoch is the one place where the very heavy and the very small are the same thing, where the entire mass of the universe is squeezed into a region smaller than a particle. There, both theories are essential at once, and when you try to make them work together, the mathematics produces nonsense, infinities that cannot be tamed. That failure is the single greatest unsolved problem in fundamental physics. There is a way to picture how strange the Planck scale is without any mathematics at all. Consider that to probe smaller and smaller distances, physicists must use higher and higher energies, which is why particle accelerators are built ever larger and more powerful. To see something the size of a proton, you need a great deal of energy focused into a tiny space. Now push that logic to the Planck length. To probe a distance that small, you would need to concentrate so much energy into so tiny a region that, according to general relativity, you would create a black hole right there at the point you were trying to examine. The very act of looking closely enough would generate a black hole that swallowed the view. This is not a limitation of our technology. It is thought to be a limitation built into nature itself, a fundamental fuzziness below which the idea of a sharply defined distance may simply not exist. The Planck length is not just small, it may be the smallest distance that has any meaning at all. Everything after the Planck epoch, by contrast, we can describe with growing confidence, and this is worth holding on to so the walls do not feel like total darkness. From a tiny fraction of a second onward, the story becomes physics we can test in laboratories, the behavior of known particles at known energies. The uncertainty is concentrated in that first impossibly brief sliver. The wall is real, but it is astonishingly thin, and on our side of it, the universe becomes legible with remarkable precision. So we now have two walls, standing almost on top of one another at the dawn of time. There is the singularity, the point of infinity that our theory both predicts and cannot survive. And there is the Planck wall, the sliver of the first second before which our physics simply has nothing to say. Everything on our list from this point forward is an attempt to see over these walls, to guess honestly at what lies on the far side. And the first, and by far the most successful, of those attempts did not come from someone staring at the singularity at all. It came from a young physicist worrying about a completely different set of problems who stumbled onto an idea that would rewrite the beginning of the universe. That idea is where we go next. Part 3. Cosmic Inflation. The idea that changed everything did not begin as a theory about the beginning of the universe. It began as a fix for three separate embarrassments, three problems that had been quietly nagging at cosmologists for years, and it solved all three at once, almost as a side effect. That idea is called cosmic inflation, and to understand what came before the Big Bang, you have to understand inflation first, because it does something radical. It takes the moment we usually call the Big Bang and demotes it. In the inflationary picture, the hot, dense fireball we have been calling the start of everything is not the start at all. It is the end of something else. Here is the core claim, stated plainly, and then we will unpack it slowly. Inflation proposes that in the first tiny fraction of a second, before the familiar hot Big Bang, The universe went through a burst of expansion so fast and so violent that no later event comes close. Not a gentle stretching, an exponential explosion of space itself, in which the universe doubled in size and then doubled again and again and again, dozens of times over, in a span of time far shorter than a trillionth of a second. A region smaller than a single proton was stretched, in that instant, to something larger than a grapefruit, and then larger still. When this furious expansion finally ended, the enormous energy that had been driving it poured out into a bath of hot particles and radiation. That outpouring, that sudden filling of space with heat and matter, is what we have always called the Big Bang. Inflation says the bang was the afterglow of something that came first. To see why anyone would propose something so extreme, we have to look at the three problems it was invented to solve, because each one is a real puzzle you can feel. The first is called the horizon problem, and it is about a strange uniformity. When we look at the oldest light in the sky, the faint glow left over from the young universe, we find that it has almost exactly the same temperature in every direction. Look one way, and it reads a particular value. Look the opposite way, across the entire sky, and it reads the same value, matched to about 1 part in 100,000. On its face, this sounds pleasant, but it is deeply mysterious. Those two opposite patches of sky are so far apart that, in the standard picture, they have never been in contact. Light has not had time to travel from one to the other in the whole history of the universe. So how did they come to agree so precisely on their temperature? Two regions that have never touched, never exchanged heat, never communicated in any way, should not match. Yet they do, everywhere, all across the sky. The second problem is called the flatness problem, and it is about a knife's edge. The geometry of the universe, the way space curves on the largest scales, appears to be almost perfectly flat, not curved inward like a sphere, not curved outward like a saddle, but flat, to a very high precision. The trouble is that this flatness is unstable. In the equations, any tiny deviation from perfect flatness in the early universe would have grown enormously over billions of years, so that today the universe should look dramatically curved one way or the other. For it to appear flat now, it must have been flat at the beginning, to an almost absurd degree, tuned to something like 1 part in many trillions. A universe that just happened to start that perfectly balanced, for no reason, is a universe that demands an explanation. The third problem is called the monopole problem, and it is about missing monsters. The physics of the extremely hot early universe predicts that certain exotic heavy particles, including magnetic monopoles, isolated north or south magnetic poles, should have been produced in vast numbers. If they had been, they would be everywhere today, and they would be easy to find. But we have never found a single confirmed one. The theory predicted a flood, and reality delivered a drought. Now watch what a brief burst of exponential expansion does to all three of these problems, because it is genuinely elegant. Take the horizon problem first. If the entire observable universe began as a single tiny patch, small enough that every part of it was in contact, snug and thoroughly mixed to the same temperature, and inflation then blew that already uniform patch up to an enormous size, then of course the sky looks the same in every direction. The opposite sides of the sky match not because they signaled to each other across the void, but because they were once the same small, cozy region before inflation flung them apart. The uniformity was established early, in intimate contact, and then stretched across the heavens. The flatness problem dissolves just as neatly. Take any curved surface and blow it up to a gigantic size, and any local patch of it looks flat. The Earth is a sphere, but the ground beneath your feet looks flat because you are seeing a tiny piece of an enormous ball. Inflation does the same thing to the whole universe. Whatever curvature space started with, Stretching it by a colossal factor irons it out, flattening it to the precision we observe. And the monopoles, if any were made, get diluted into oblivion, spread so thinly across the vastly expanded space that we would be lucky to find even one in the entire visible universe. 3 problems, 1 mechanism. That combination is what made physicists sit up. But the most beautiful part of inflation, the part that turned it from a clever fix into something that feels almost like a scientific creation story, is what it says about where galaxies came from. In the quantum world, nothing is ever perfectly still or perfectly smooth. Even the field driving inflation had tiny, unavoidable fluctuations, little quantum ripples flickering in and out. As inflation stretched space, it stretched these microscopic fluctuations along with it, blowing them up to astronomical size and freezing them into the fabric of the cosmos as faint variations in density. Some regions ended up very slightly denser than others, and over the following billions of years, gravity went to work on those slight overdensities, pulling in more matter, growing them, until they became the seeds of everything. Every galaxy, every cluster of galaxies, the entire vast cosmic web of structure, grew from quantum fluctuations that inflation enlarged from the subatomic to the cosmic. The largest structures in existence are the frozen echoes of the smallest possible jitters. When you look at a galaxy, you are looking at a quantum flicker, magnified beyond all recognition and written across the sky. The story of who discovered this is worth telling with care, because it is a story of a good idea that arrived broken and had to be repaired by several hands. In late 1979, a young American particle physicist named Alan Guth was wrestling with the monopole problem when he realized that a period of what he called inflation, a burst of exponential expansion, would solve it, and the horizon and flatness problems besides. He published the idea in 1981, and he gave it its name. But Guth was the first to point out that his original version had a serious flaw. In his model, the inflating phase would not end gracefully or uniformly. It would end in a chaotic, patchy way that would leave the universe a mess, nothing like the smooth cosmos we see. He had found a mechanism with the right shape, but the wrong ending. The repair came quickly, from 2 directions at once. In 1982, the Russian physicist Andrei Linde found a way to make inflation end smoothly and completely and independently. The American physicists Andreas Albrecht and Paul Steinhardt arrived at essentially the same solution. Their version came to be known as new inflation, and it fixed the graceful exit problem that had troubled Guth's first attempt. Then, Linde pushed further. In 1983, he introduced what he called chaotic inflation, showing that inflation did not require some special, finely arranged starting condition. It could begin from a wide range of generic, even random, initial states. This made the theory far more robust. Inflation no longer needed the universe to be set up just right. It could get going almost anywhere, under a broad set of circumstances, which is a very desirable trait in an explanation. Then came the tests, and this is where inflation earned its place at the center of cosmology. A theory that only explains what we already knew is merely tidy. A theory that predicts what we have not yet measured and turns out to be right is powerful. Inflation made specific, detailed predictions about the pattern of those frozen quantum fluctuations, about exactly how the temperature of the oldest light should vary from place to place across the sky. And over 3 decades, a succession of increasingly precise instruments went looking. The COBE satellite, in the early 1990s, first detected the faint temperature variations at the level inflation suggested. Then the WMAP satellite mapped them in far greater detail. Then the Planck satellite, reporting through the 2010s, measured them with exquisite precision. Prediction after prediction held up. The sizes of the fluctuations, The way they were distributed across different scales, the subtle statistical fingerprints, all matched what inflation had forecast. It was a remarkable run of success for an idea that had started as a fix for missing particles. Let us pause on the sheer scale of what inflation proposes, because the numbers are worth sitting with, each one made real by comparison. During inflation, the universe is thought to have expanded by a factor of at least 10 to the 26, and quite possibly far more. That means the entire observable universe today, all 90-odd billion light-years of it that we can survey, traces back to a patch of space smaller than a single atom. Everything you have ever seen, or will ever see, grew from a seed of almost nothing, and all of it happened fast beyond comprehension, in a window running from around 10 to the minus 36 seconds to about 10 to the minus 32 seconds after time zero. The exponential doubling ran through dozens of cycles before the universe was a trillionth of a second old. By the time the first full second had elapsed, inflation was ancient history, an event already unimaginably far in the past. So inflation gives us the closest thing science has to a genuine account of how everything we see came to be. From a speck, smaller than an atom, stretched in an instant to cosmic size, seeded with the quantum flickers that would become galaxies. It is a triumph, and it deserves the standing it has. But notice, carefully, what it does to our original question. Inflation does not tell us what came before the beginning. It moves the beginning. The hot Big Bang is now the end of inflation, not the start of the story. So the question simply steps back one pace and asks again, with more force than before, what came before inflation? What lit the fuse? Did inflation itself have a beginning, or could it stretch back forever? It is worth lingering on how strange the inflationary field would have to be, because it points to physics we still do not understand. Ordinary matter, when space expands, thins out and its influence weakens. But the field that drives inflation does the opposite. As it fills space, it maintains a nearly constant energy density, even as space grows, which means that the more space there is, the more total energy there is to keep the expansion going. This is the engine of the runaway. It is a form of energy that, in effect, pushes space apart and feeds on its own expansion. The nearest thing we know of in the present universe is dark energy, the mysterious influence driving the current accelerating expansion, which is far gentler, but shares that same strange quality of not diluting as space grows. Some physicists suspect the two may be related, that inflation was an early, ferocious cousin of the dark energy we see today, though no one has established the connection. The precision of inflation's success is easy to state, but hard to feel. So consider what the satellites actually measured. When COBE, and then WMAP, and then Planck mapped the oldest light, they were measuring temperature differences from place to place across the sky that amount to about 1 part in 100,000, variations of a few millionths of a degree on a background of 2.7 degrees. Inflation predicted not just that these variations should exist, but the detailed way they should be distributed across large and small patches of sky, a specific statistical signature. And when the measurements came in, the pattern matched. The tiny hills and valleys in the temperature of the oldest light lined up with what a burst of quantum-seeded expansion should produce across a range of scales with a consistency that turned a great many skeptics into believers. It is one thing to propose that galaxies grew from quantum fluctuations. It is another to predict the precise fingerprint of those fluctuations and then find it, written across the entire sky, decades later. Yet, for all this success, it is important to be clear that inflation is a framework more than a single theory, and this matters for everything that comes after. There is not one inflation but many versions, differing in the details of the field that drives them, and they make somewhat different predictions. This flexibility is part of why inflation has been so hard to either fully confirm or cleanly rule out. Critics point to it as a weakness, arguing that a theory with so many variants can accommodate almost any result. Defenders respond that the core predictions, the ones all versions share, have held up beautifully. This tension between a framework's explanatory power and its ability to be decisively tested will follow us all the way to the final part of this list. And there is a further wrinkle, one that is going to open the next door. Inflation, in most versions, turns out to be strangely difficult to stop. Once it starts, it shows a tendency to keep going. Somewhere. Always. That single stubborn feature, the reluctance of inflation to ever fully end, leads to one of the most vertiginous ideas in all of science. An idea that takes our one universe and multiplies it beyond counting. That is where we turn next. Part 4. Eternal Inflation and the Bubble Multiverse. Once you accept inflation, a strange conclusion follows, almost against your will. It is not something the theorists set out to find. It is something the equations kept insisting on, no matter how the physicists tried to talk them out of it. The conclusion is this. In most versions of inflation, the process does not switch off everywhere at the same time. It cannot, and once you understand why, you find that our Big Bang was very likely not the only one, and perhaps not even a rare one. It may be one of an endless number, still happening now, forever, in a vast arena we can never reach. To see how this works, we have to remember what drives inflation. It is a field-filling space, holding a large amount of energy, and that energy is what powers the runaway expansion. Inflation ends in a given region when the field decays, when it rolls down to a lower energy and releases its stored energy as a hot bath of particles, the local Big Bang. But here is the catch. The field is quantum, and quantum things are subject to constant random fluctuations. In some regions, the field decays quickly, and inflation ends there, forming what physicists call a bubble, a pocket of ordinary space where a hot universe like ours begins to unfold. But in the surrounding regions, the field, by chance, has not yet decayed, and that surrounding space keeps inflating, doubling and doubling, at a staggering rate. Now weigh those two processes against each other. Bubbles of normal space form here and there, where inflation has ended, but the space between the bubbles is expanding exponentially, faster than the bubbles can ever fill it. So no matter how many bubbles form, the inflating region between them grows faster still, always making room for more. Inflation, once it starts, never fully ends. It ends locally, in patches, producing bubble after bubble, but globally it goes on forever, an eternally inflating background continually sprouting new pocket universes. This is called eternal inflation, and it is not an exotic add-on. For many of the most natural models of inflation, it is simply what the mathematics does when you follow it honestly. If eternal inflation is correct, then our question about what came before the Big Bang now has a concrete and startling answer. Before our Big Bang, there was the eternally inflating background out of which our bubble condensed. Our entire universe, everything we can observe, is the interior of one bubble that nucleated in that endless inflating sea. And our bubble is not special. Others were forming before ours, and others are forming now, and others will keep forming without end, each one a universe in its own right, each one beginning with its own local bang as the field decays within it. The thing we have always called the universe becomes, in this picture, a single bubble in a boundless froth of universes. This froth has a name that has escaped the physics journals and entered ordinary language. It is the multiverse. Picture the eternally inflating background, though picturing it strains everything, because there is nothing ordinary to compare it to. All around, space is doubling and redoubling at a rate beyond thought, a smooth, featureless, furiously stretching expanse holding its enormous energy. Then, at one point, the field slips. It decays, and in that spot, a bubble opens, a pocket of calmer space where inflation has stopped and energy is flooding out into heat and matter and light, a new universe catching fire from within. You are inside that bubble at the instant it forms. This is our bubble. This is our Big Bang, seen from the outside, a single blister opening in an endless, inflating skin. And even as it opens, the space around it is expanding so much faster than the bubble can grow that the walls race away from you at more than the speed of light, sealing the new universe off from all the others forever. Beyond your bubble, out in the froth, other bubbles are opening too, countless others, each one a cosmos, each one walled away by the same runaway expansion. You will never see any of them. You cannot. The gap is growing faster than any signal could ever cross it. That last point is the hard, defining feature of this multiverse, and it cuts two ways. The bubbles are, by construction, unreachable. The inflating space between any two of them expands faster than light can travel, which means no signal, no probe, no observation of any kind can ever pass from one bubble to another. The other universes are not far away in the ordinary sense, where far means a long journey. They are absolutely, permanently cut off. This makes the multiverse of eternal inflation a peculiar kind of scientific idea. It emerges from a well-tested theory, inflation, as a natural consequence. And yet, its central claim, the existence of the other universes, seems to lie forever beyond the reach of any experiment we could perform from inside our own bubble. The other bubbles need not even resemble ours. When the inflating field decays, the details of how it settles can differ from bubble to bubble, and those details can determine the basic properties of the resulting universe. The masses of particles, the strengths of the forces, the amount of energy woven into empty space, all of these might come out differently in different bubbles. Most of the resulting universes would likely be sterile, hostile places, where the constants of nature forbid the formation of stars or atoms or chemistry. A few, here and there, might come out balanced in the narrow way that permits galaxies and worlds, and eventually, someone to wonder about it. Our bubble is one of those. The recognition that inflation is eternal came early. Alexander Vilenkin identified the eternal character of inflation in 1983. And André Linde, who had done so much to make inflation work in the first place, developed the picture extensively through the following years. Linde's version, sometimes called eternal chaotic inflation, made the endlessly branching multiverse a natural outcome of the very same equations that were, at that moment, matching the oldest light in the sky so beautifully. This was the uncomfortable bargain at the heart of the theory. The framework that best explained our own universe seemed to come bundled with a prediction of infinitely many others, whether the physicists wanted them or not. Not everyone accepted the bargain gladly, and the objections are serious ones, worth stating fairly. Because the other bubbles cannot be observed, some physicists argue that eternal inflation drifts away from science and toward metaphysics. If the multiverse contains infinitely many universes, with every possible variation, then in some sense anything that can happen does happen, somewhere, and a theory that permits everything may end up predicting nothing in particular. Strikingly, one of the sharpest critics is Paul Steinhardt, one of inflation's own founding architects, who came to feel that the eternal multiverse drains inflation of the predictive power that made it worth believing. The debate over whether eternal inflation is profound physics or an untestable overreach is not settled. It is being argued in the literature right now. There is a further twist, and it is one that keeps our original question alive rather than answering it. You might think that an eternally inflating multiverse, going on forever, would at least be past eternal as well, stretching back infinitely so that there was never any beginning to explain. But in 2003, three physicists, Arvind Borde, Alan Guth, and Alexander Vilenkin, proved a theorem that says otherwise. They showed that any universe, or multiverse, that is on average expanding, cannot be extended infinitely into the past. Even the endless froth of eternal inflation, for all its boundless future, must still have a past boundary, a beginning to the whole thing. So even the multiverse does not escape the need for a start. It pushes the beginning further back, out beyond our bubble, into the inflating sea. But it does not abolish it. The beginning to the beginning is still there, waiting. And then there is the conclusion that many people find hardest to swallow, the one that hints something in the framework may be incomplete. In an infinite multiverse, with infinitely many bubbles and every possible variation playing out, everything permitted by the laws happens not just once, but infinitely often. That includes, if you follow the logic strictly, exact copies of our universe, exact copies of our galaxy, exact copies of you, sitting exactly where you are, hearing exactly these words, making exactly this choice, infinitely many times over, scattered through the endless froth. Most physicists regard this conclusion as a warning sign rather than a discovery, a hint that our tools for reasoning about infinity are failing us somewhere. It is called, in the technical literature, the measure problem, the unsolved difficulty of how to make sensible predictions when infinitely many outcomes all occur. So the multiverse of eternal inflation leaves us in a strange and humbling place. It offers a real answer to what came before our Big Bang, the eternally inflating background, and it does so as a natural consequence of our best theory of the early universe. But it purchases that answer at the cost of infinitely many other universes we can never see, a beginning that still refuses to go away, and a swarm of copies of ourselves that many suspect cannot really be right. The vertigo it produces is not the old vertigo of being small in a large space. It is a newer and stranger vertigo of being small in the count of universes. One bubble among endless bubbles, one story among infinitely many. The idea of infinitely many other universes can feel like pure fantasy, so it is worth being clear about why serious physicists take it seriously rather than dismissing it. No one set out to invent the multiverse. It arrived unbidden, as a consequence of equations that were doing an excellent job elsewhere. This is a recurring pattern in physics. A theory built to explain one thing turns out to predict something else, something no one asked for, and the question becomes whether to trust the theory far enough to accept the unexpected prediction. Antimatter was predicted this way, as an uninvited solution to an equation, before it was ever observed. The multiverse of eternal inflation has the same character. It is not an assumption bolted on. It is what the mathematics of inflation appears to insist upon when you refuse to look away. That is why it cannot simply be waved off, even by those who find it deeply uncomfortable. There is a subtle point about time and simultaneity in the eternally inflating picture that deepens the strangeness. When we say bubbles are still forming now, the word now is doing something it cannot quite handle. Because in a space expanding faster than light can cross it, there is no shared present moment stretching across the whole multiverse. Each bubble has its own time, its own history, its own sense of before and after, and these cannot be lined up into a single, universal clock. Our bubble is billions of years old from the inside, with its own long history. From the vantage of the inflating background, that entire history occupies a region that is still, in some sense, being sealed off. The ordinary intuition that everything that exists shares a common present simply fails here. The other universes are not elsewhere in our space. and not simply earlier or later in our time. They are outside the framework in which our words for place and moment were built to work. This is also where the deepest philosophical unease about eternal inflation lives, and it is worth stating plainly rather than hiding. A theory that predicts everything that can happen does happen, somewhere, infinitely, often, is a theory that has a very hard time being surprised by anything. If someone asks what such a theory forbids, the honest answer is unclear, and a theory that forbids nothing is a theory that is difficult to test. Some of the sharpest minds in physics have spent years trying to find a way to extract ordinary, testable predictions from the eternal multiverse, to define what is typical or likely within the infinite froth. The problem has proven remarkably stubborn. It remains one of the central open questions hanging over the whole inflationary picture, unresolved and much argued over. If a universe can appear as a bubble in an inflating sea, seemingly without anyone lighting a match, it is worth asking a more basic question. Does a universe need a cause to begin at all? Could the whole thing simply come into being, uncaused, out of nothing whatsoever? That is the next idea on our list, and it is one of the boldest of them all. Part 5. The universe from nothing. There is a class of models that answers the question of what came before the Big Bang in the most radical way imaginable. They answer that nothing came before, not because time began at the Big Bang in some fuzzy sense, but because the universe came into existence spontaneously, as a quantum event, from a state with no space, no time, and no matter at all. The universe, in this view, did not emerge from something earlier. It simply appeared, uncaused, the way certain events in the quantum world happen with no prior reason. To many people, this sounds like a contradiction or a trick. It is neither. It is a serious proposal, and it rests on one of the genuine strangenesses of physics. To follow it, you have to first accept something that quantum mechanics established a century ago and that has been confirmed in laboratories ever since. At the smallest scales, events can happen without a specific cause. A radioactive atom decays at a particular instant, and there is no hidden reason, no trigger, that made it happen then, rather than a moment earlier or later. It is genuinely spontaneous, governed only by probabilities. Empty space itself is not truly empty, but seethes, with particles flickering into being and vanishing again, borrowing energy briefly from the quantum vacuum and paying it back. In the quantum world, the old rule that every event must have a cause is simply not true. Things happen, sometimes, for no reason at all, within the bounds that probability allows. The models of cosmic creation from nothing take this principle and apply it to the boldest possible case, to the origin of the universe itself. They propose that a tiny universe can come into being through a quantum process, appearing spontaneously with a definite, calculable probability, from a condition that is not empty space but the genuine absence of space and time. And here we have to be very careful about the word nothing, because it is doing an enormous amount of work and it is easy to misunderstand. The nothing in these models is not a vast empty room waiting for a universe to appear in it. An empty room is already something. It has space. It has volume. It has the potential for things to happen within it. The nothing these models describe is deeper and stranger than that. It is the absence of space itself, the absence of time itself, a state in which there is no where and no when, no stage on which anything could sit. The claim, then, is that the laws of quantum physics permit a small, closed, finite universe to appear from that true nothing, complete with its own space and its own time, ready to begin expanding. And because there is no time before such an event, there is no before at all. This is the point that dissolves the original question rather than answering it. The universe does not begin in time, as if there were a clock already ticking and at some moment the universe switched on. Time begins with the universe, as part of the same event. Ask what came before, and the honest reply is that the word before has no referent, because before is a direction in time, and time is precisely one of the things that did not yet exist. The details of how such a thing could work were laid out by the physicist Alexander Vilenkin, whom we have already met as the man who recognized that inflation is eternal. In a landmark paper in 1982, Vilenkin proposed the creation of universes from nothing through a process called quantum tunneling. Tunneling is a real and well-understood quantum phenomenon. A particle facing a barrier it does not classically have enough energy to cross can, with some probability, simply appear on the other side, having passed through a region it could never have entered by ordinary means. It is how the sun shines, how certain radioactive decays proceed, how some electronic devices function. Vilenkin's insight was to imagine the universe itself tunneling, not through a barrier in space, but from zero size into a small, finite, expanding cosmos, passing through a quantum barrier that separates non-existence from existence. On the far side of that barrier sits a tiny universe, which can then, through something like inflation, grow to the vastness we inhabit. Notice how this idea links up with the earlier ones rather than replacing them. A universe born by tunneling would naturally start out extremely small, near the Planck scale, and it would need a mechanism to grow to cosmic size. Inflation is exactly such a mechanism, so the picture that emerges is a chain. A universe tunnels into existence from nothing, tiny and closed. Inflation then seizes it and stretches it, in that first fraction of a second, into something enormous. And then inflation ends, and the hot Big Bang we know pours out. Creation from nothing supplies the very first step, the appearance of the seed. Inflation supplies the growth. Together, they sketch a complete story that never requires an earlier universe or a prior cause. This idea reached a wide public through the physicist Lawrence Krauss, whose 2012 book, titled simply A Universe from Nothing, argued that modern physics makes the spontaneous origin of a universe not merely conceivable, but, given the laws, perhaps even likely. Krauss made the case with force and clarity, and the book provoked a genuine and useful argument, one worth understanding because it exposes the deepest tension in the whole idea. Critics, including a number of philosophers, pointed out that the nothing of physics is not quite the nothing of the old question. Vilenkin's tunneling, and any quantum creation event, still presupposes the laws of quantum physics. The rules that permit the tunneling, the mathematics that assigns it a probability, these are already in place. So the universe may come from no space, no time, and no matter. But it does not come from no laws. And that, the critics say, is not truly nothing. It is a very austere something, a something consisting of physical law with nothing yet for the law to act upon. This objection does not defeat the models, but it sharpens what they are really claiming, and it exposes a question that physics may not be able to answer at all. If a universe can come from nothing because the laws of physics allow it, then where did the laws come from? Why is there quantum mechanics rather than no quantum mechanics? A framework of rules rather than a true and total blank? This is arguably the hardest question in this entire video, and it is not clear that any experiment could ever touch it. The models of creation from nothing tell us, with mathematics, how a universe might appear given the laws. They are silent, as perhaps physics must be, on why there are laws for anything to be given. There is one more subtlety here. a genuine open dispute among serious physicists that shows how unsettled this territory remains. Vilenkin's tunneling proposal is not the only account of how a universe might begin as a quantum event. There is a rival, the no-boundary proposal of James Hartle and Stephen Hawking, which we will meet in the very next part. The two proposals use strikingly similar mathematics, the mathematics of assigning a probability to an entire universe. But they differ in a crucial technical choice, and because of it they predict opposite things about which kinds of universes should be most probable. In Vilenkin's version, one class of universes is favored. In the Hartle-Hawking version, the favoring runs the other way. Physicists have argued for decades about which sign in the equation is the correct one, and the argument is not resolved. Two of the most respected attempts to describe the birth of the universe from nothing disagree, using the same tools, about the most basic question of what should have been born. To feel the force of the idea that events can happen without a cause, it helps to sit with how thoroughly quantum mechanics has established it. This is not a loophole or a matter of hidden information we simply have not found yet. Physicists spent decades testing whether there might be secret variables underneath quantum randomness, hidden gears that would restore ordinary cause and effect. A series of increasingly precise experiments, building on a theorem proved by the physicist John Bell in the 1960s, has ruled out the most natural versions of that hope. The randomness appears to be woven into the fabric of reality, not a mask over some deeper determinism. When a particle decays, there is genuinely no prior reason it decayed at that instant. If nature permits truly uncaused events at the smallest scale, then the proposal that the universe itself is such an event is not a violation of physics. It is an extension of a principle physics has confirmed again and again. The notion that empty space is not truly empty deserves a moment, because it makes the idea of creation from nothing feel less impossible. What we call the vacuum, the emptiest possible region, is in quantum physics a restless, seething thing, full of fields that cannot ever be perfectly still, full of particle pairs flickering into being and annihilating again before they can be caught. This is not speculation. The subtle effects of that quantum restlessness have been measured in the laboratory, in tiny forces between metal plates and in minuscule shifts in the light emitted by atoms. If the vacuum, which looks like nothing, is actually a churning sea of quantum activity, then the leap to imagining that a whole universe might emerge from an even deeper kind of nothing, the absence of space and time themselves, becomes a little less unthinkable. The everyday intuition that nothing can come from nothing was built for a world of solid objects. It was never tested against the quantum vacuum, and there it seems to fail. Still, the honest scientist admits where the mystery truly bites, and it is worth naming clearly. Even the most successful account of creation from nothing describes a universe emerging according to quantum law. The law is the one thing that is never explained, only assumed. Why there should be quantum mechanics at all, why reality should come equipped with rules that permit universes to tunnel into being, is a question that may lie permanently beyond the reach of physics, because physics works by discovering laws and using them, not by explaining why there are laws in the first place. This is not a flaw in the theory, so much as a boundary of the entire enterprise, and recognizing it is part of thinking clearly about the beginning. So creation from nothing offers the cleanest possible answer to what came before the Big Bang. Nothing did, and the question itself dissolves, because time and cause both began with the universe. It is an answer that overturns the oldest intuition we have, the deep conviction, older than science, that nothing comes from nothing, that everything that begins must have been brought about by something before it. Whether that overturning strikes you as liberating or as vertiginous may be one of the most personal reactions in all of cosmology. But the second of the two great quantum creation proposals took a gentler path to a similar destination. Rather than saying the universe popped out of nothing, It suggested that the very idea of a first moment might be an illusion, because near the beginning, time itself curves quietly closed. That is the no-boundary proposal, and it is where we go next. Part 6. The no-boundary proposal. Some questions are best answered not by solving them, but by showing that they were malformed to begin with. That is the strategy behind one of the most elegant ideas in the whole of cosmology, an idea proposed by Stephen Hawking, together with the physicist James Hartle in 1983. It is called the no-boundary proposal, and its claim is quietly stunning. It suggests that the universe has no initial boundary in time at all, no first moment, no sharp edge where everything switched on, no singularity. Instead, the universe is smooth and finite, curving gently closed on itself near the origin, with no beginning point to be found anywhere on it. And the reason we keep failing to find what came before the Big Bang, in this view, is that the question quietly stops meaning anything as you approach the start. To understand how time could have no beginning, and yet the universe still be finite in age, Hawking offered an analogy so good that it has been repeated ever since, and it repays slow attention. Think about the surface of the Earth, and think about the direction south. You can travel south, and keep traveling south, and the concept works perfectly well for a very long time. But then you reach the South Pole. The South Pole is a real, definite place. There is nothing vague about it, and yet, standing there, you cannot go any further south. Not because you have hit a wall, not because a fence stops you, but because south has simply run out of meaning. There is no point on the Earth that is further south than the South Pole. The question, what lies south of the South Pole, has a definite answer, and the answer is that the question does not apply. It is not that the territory is hidden. It is that there is no territory, and no lack of territory either. The direction has ended. Hawking's proposal is that the beginning of the universe is like the South Pole, but for time. As you trace time backward toward the origin, you approach a kind of pole, a smooth rounding off, and at that pole, the direction we call before simply ceases to apply. Asking what came before the Big Bang, he said, is like asking what lies south of the South Pole. It is a real limit, but it is not a wall with something on the other side. It is the place where the question gently dismantles itself. There was no time before the Big Bang, because before ran out, the way south runs out at the pole. And there is nothing beyond it, not even an empty nothing, because beyond has lost its footing. The mathematical device that makes this work is subtle, and it carries a name that sounds stranger than it is. It is called imaginary time. In ordinary physics, time and space behave differently. But Hartle and Hawking found that if you perform a particular mathematical rotation, treating time, near the very beginning, as though it were another dimension of space, the singularity smooths away. The sharp, infinite point at the start is replaced by a gentle, rounded cap, like the smooth pole of a sphere, rather than the tip of a cone. In this imaginary time, the universe has no edge, no boundary, nowhere that could be called the first instant. The ordinary time we live in and experience, the time that flows from past to future, emerges from this rounded bottom. But at the bottom itself, there is no first tick to point to, because the roundness has no corner. There is something almost consoling about what this does to the beginning. In the singularity picture, the origin is a moment of crisis, a point of infinite violence where physics tears itself apart. In the no-boundary picture, the origin is not dramatic at all. It is smooth. It is finite. It is complete. The universe simply is curving closed like the surface of a ball, which is finite in size and yet has no boundary you could ever fall off. You could wander the surface of the Earth forever and never reach an edge, because a finite thing can be perfectly boundaryless. The no-boundary universe is like that. but in time as well as space. Finite in the past, yet with no first moment, the way the Earth's surface is finite in area, yet with no rim. To carry a claim this large, Hartle and Hawking wrote down one of the boldest equations ever attempted. It assigns a probability to the entire universe, considered as a single object, computed by adding up all the smooth, boundaryless shapes the universe could possibly have taken. It is called the wave function of the universe. In ordinary quantum mechanics, a wave function describes the probabilities for a particle, whether it is here or there. Hartle and Hawking applied the same idea to everything at once, to the whole cosmos, in a single grand expression. Whatever one thinks of the proposal, the ambition of writing down a wave function for the entire universe is difficult to overstate. It is an attempt to treat the birth of reality itself as a quantum question with a calculable answer. It is impossible to tell this part of the story without pausing on the man at its center. Stephen Hawking spent almost his entire adult life inside a body that was failing him piece by piece, a motor neuron disease steadily taking his movement, his voice, nearly everything but his mind. And it was during those decades, confined to a chair, communicating at last through a single cheek muscle and a computer, that he reached for the one place in all of existence with no boundaries at all. There is something almost unbearably fitting in it. A man who understood confinement more intimately than almost anyone, who knew from the inside exactly what a wall and a limit and an edge really were, devoting the full power of his mind to proving that time, at least, has no edge. That the universe, at its origin, is boundless and smooth and without any cruel first wall. He carried the South Pole analogy to millions of readers in his 1988 book, A Brief History of Time, and in doing so, he offered the world not just a piece of physics, but a particular kind of comfort, the idea that the beginning need not be a place of crisis, that it can be complete and gentle and whole. He pursued refinements of the proposal into the final years of his life. It is hard not to feel that the question mattered to him in a way that went beyond the equations. The no-boundary proposal became one pole of a long, friendly rivalry, the other pole being Vilenkin's creation from nothing that we met in the previous part. Both use the mathematics of a wave function of the universe. Both try to describe the birth of the cosmos as a quantum event, but they make opposite choices about the boundary conditions, about how to set up the calculation, and so they disagree about which universes should be most likely. The argument between the Hartle-Hawking picture and the Vilenkin picture ran for decades and was never cleanly settled. Late in his life, Hawking co-authored work that itself questioned whether the no-boundary wave function really predicts a smooth, orderly universe like ours, or whether it might favor something quite different. Even its own architect kept probing it, testing it, refusing to let it rest as a finished thing. And that unfinished quality is honest, because the proposal raises questions it cannot answer. Is imaginary time a real feature of the world, an actual description of how the universe is near its origin? Or is it a purely mathematical trick that happens to give sensible results, a clever change of variables with no deeper meaning? Physicists genuinely disagree. And does the no-boundary wave function actually predict a universe like the one we see, with its particular smoothness and structure? Some later analyses, including the work Hawking himself joined near the end, cast doubt on it. The proposal is beautiful, and it may be right, but it is not confirmed, and it may never be, because it speaks about a regime we cannot reach. The South Pole analogy rewards a second, slower pass, because it does more work than it first appears. Notice that the South Pole is not a defective or broken place. Nothing is missing there. A traveler standing at the pole is on perfectly ordinary ground, and the smoothness of the Earth is complete and unbroken at that point. It is only the direction, the concept of further south, that has quietly run out. In the same way, the no-boundary universe is not defective or torn at its origin. The origin is smooth, complete, unremarkable ground, and it is only the direction we call before that ceases to apply. This is a profoundly different picture from the singularity, where the origin is a place of infinite violence and breakdown. Hawking's proposal replaces a catastrophe with a smooth cap, a beginning that is not a rupture but a gentle rounding, and it does so precisely to avoid the singularity that his own earlier theorems had seemed to demand. The man who helped prove the beginning must be singular spent his later years arguing it might be smooth after all. There is a reason imaginary time, strange as it sounds, is not simply made up, and understanding it makes the proposal feel less like a trick. In the mathematics that unites space and time, there is a deep and well-known relationship in which treating time as if it were a spatial dimension is not an arbitrary move, but a natural one, used routinely by physicists to solve problems in ordinary situations far from any cosmic origin. The technique is standard and trusted in many corners of physics. What Hartle and Hawking did was apply this respectable tool to the beginning of the universe. And notice that, in this regime, it smooths the singularity into a rounded cap. Whether that smoothing describes physical reality or is only a calculational convenience is exactly the open question. But the technique itself is not exotic. It is a familiar instrument, turned, for the first time, on the birth of everything. It is also worth appreciating what a strange and lonely kind of ambition the wave function of the universe represents. In ordinary quantum mechanics, there is always an outside, an observer, or an apparatus, separate from the system being described, measuring it, collapsing its possibilities into definite outcomes. But the universe, by definition, has no outside. There is no external observer, no apparatus beyond it, nothing to measure it from beyond its own edge. To write down a wave function for the entire universe is to attempt something quantum mechanics was never designed to do, to describe a system that contains everything, including any possible observer. This is one of the deepest conceptual puzzles in the whole subject, and it is unresolved. It means that even if the no-boundary proposal is mathematically correct, we are still not entirely sure how to interpret what it is telling us, because the usual rules for reading a wave function assume a vantage point that, for the universe as a whole, does not exist. What the no-boundary proposal leaves us with is a different way of holding the question. It does not tell us what came before. It suggests that before, near the origin, is the wrong word. The way south is the wrong word at the pole. The universe, in this picture, has no first moment to have anything before it. It is finite, smooth, self-contained, and boundless all at once, but not everyone is willing to let the beginning round itself away so gently. If time can curve closed on one side, others have asked, why can it not have another side entirely? A whole earlier universe on the far side of the beginning, which contracted, reached a minimum, and rebounded into ours? That idea replaces the beginning not with a smooth pole, but with a passage, a bounce from a universe that came before. And that is where we turn next. Part 7. The Big Bounce. The models we have met so far either dissolve the beginning or conjure it from nothing. The next family does something different, and to many people more satisfying. It keeps the idea of a before and fills it with a whole universe. In these models, our Big Bang was not a birth, but a rebound. A previous universe existed, contracting inward under its own gravity, growing hotter and denser until it reached a minimum size, and then, instead of crushing itself into a singularity, it bounced, it reversed. It began to expand again, and that expansion is what we call the Big Bang. This is the Big Bounce, and it answers our question with unusual directness. What came before the Big Bang was a collapsing universe on the far side of the bounce. The obvious objection is the one we started this whole video with. If you run a universe backward, general relativity says it collapses to a singularity, a point of infinite density. And there, the equations shatter. How can anything bounce through infinity? The answer is that in these models, the collapse never reaches infinity, because a deeper theory takes over before it can. And the leading candidate for that deeper theory is a genuinely radical reimagining of what space is. It is called loop-quantum gravity, and its cosmological application is called loop-quantum-cosmology. The central idea of loop-quantum gravity is that space is not smooth and infinitely divisible, the way it appears, and the way general relativity assumes. Instead, space is made of discrete, finite chunks, indivisible atoms of volume, woven together into a fine network. There is a smallest possible unit of space, just as matter has smallest units in its atoms, and light comes in smallest units called photons. On the scales we live at, this granularity is far too fine to notice, and space looks perfectly continuous. But near the extreme densities of the early universe, the grainy quantum structure of space becomes everything. And it has a dramatic consequence. Because space cannot be compressed below the size of its smallest chunks, there is a limit to how densely matter can be packed. Squeeze hard enough, and the quantum structure of space pushes back. Gravity, which is attractive at ordinary densities, effectively becomes repulsive at the extreme, halting the collapse and flinging the universe back outward. The bounce is not put in by hand. It falls out of treating space as quantum. Notice how completely this removes the infinity. In loop-quantum cosmology, there is no singularity anywhere. The density at the moment of the bounce is enormous, but strictly finite, capped at a specific value set by the granular structure of space itself, on the order of what physicists call the Planck density. That figure is almost beyond comprehension. Roughly 10 to the 96th times the density of water, a compression so extreme that a single grain of it would outweigh whole galaxies. But it is finite. It is a definite number, not an infinity. And because it is finite, the equations do not break. They keep working straight through the moment that classical physics called the beginning, describing a universe that was contracting before, reaches maximum density at the bounce, and expands afterward, all in one continuous story with no tear in it. The universe on the far side of the bounce, the one that was collapsing, need not have looked anything like ours. The bounce can scramble the details, resetting or reshaping the conditions, so the prior universe might have had a different arrangement of matter, a different history, a different character entirely. It is not required to be a mirror image of what came after. All that carries through, in the simplest models, is the fact of a smooth passage from contraction to expansion, a universe breathing in and then breathing out. The modern version of this idea was launched by the physicist Martin Bojewald in 2001, when he showed that applying the techniques of loop quantum gravity to the universe as a whole removes the Big Bang singularity. This was a striking result, because it suggested that the beginning, the great unreachable wall, might not be a wall after all, but a doorway that the right theory could walk straight through. Over the following years, the framework was developed with much greater rigor and precision by Abhay Ashtekar, one of the founders of loop quantum gravity, working with Tomasz Pawlowski and Parampreet Singh. Their detailed models, published through the mid-2000s, demonstrated a concrete quantum bounce, tracking a contracting universe as it passed smoothly through its moment of maximum density and out into expansion. What had been a hopeful idea became a worked example, a specific, calculable model of a universe surviving its own beginning. The appeal of the bounce is easy to feel. Where general relativity produces an infinity and quits, loop quantum cosmology produces a large but finite number and keeps going. It does not tame the singularity so much as abolish it, replacing the sharp point of infinite density with a well-defined moment of maximum compression through which physics can be followed continuously. And it does this not by adding some new ingredient chosen to make the problem go away, but as a natural consequence of taking the quantum nature of space seriously. If space really is granular, then infinite density is impossible, and a bounce becomes not just allowed, but expected. If the bounce is real, the implications reshape the whole story of cosmic history. The Big Bang was not the birth of everything but a single event within a much longer history, possibly one bounce among many. A universe that has expanded and contracted and expanded again across an immense span of time. Our 13.8 billion years would then be merely the latest cycle, the current breath, with unknown numbers of previous universes stretching back behind the bounce. And it implies something profound about the nature of space. The same conclusion loop quantum gravity was built on. There is a smallest possible volume, an atom of geometry, below which the question how much smaller has no answer. In exactly the way that asking for half a photon or half an atom of gold has no answer. Space, at the deepest level, comes in pieces. But the bounce shares the honest uncertainty of every model on this list. Loop quantum gravity is a serious, carefully constructed contender for the theory of quantum gravity, but it is not confirmed. It is one approach among several, and like its rivals, it has not been tested against experiment in the regime where it matters. We do not yet know whether space is truly granular in the way it proposes, and there is a further, tantalizing question. If a universe existed before the bounce, could any trace of it have survived the crossing? Could the collapsing universe have left some faint imprint, some fossil, in the oldest light of ours, a message from before the beginning? Or does the bounce, in its violence, erase its own history, leaving the prior universe forever unknowable? That question will return with force at the end of this video, when we ask what any of these models could ever leave for us to find. The idea that space itself comes in indivisible pieces is so contrary to intuition that it is worth dwelling on how loop quantum gravity arrives at it. In this framework, the smooth space of everyday experience is woven from a network of relationships, and area and volume turn out to be quantized, meaning they can only take on specific, discrete values rather than any value at all. There is a smallest possible area, a smallest possible volume built into the structure of reality, in the same way that electric charge comes only in whole multiples of a basic unit and never in between. Space, in this view, is not a smooth, continuous backdrop, but something closer to an intricate fabric woven from finite threads. And the smoothness we perceive is the blur of countless tiny pieces seen from far away, the way a photograph in a newspaper looks continuous until you bring it close and see the dots. If this is right, then the question of what happens when you compress the universe toward a point answers itself. You cannot compress space below the size of its smallest pieces. And so the infinite density of the singularity becomes impossible not by decree, but by the very grain of space. One of the appealing features of the bounce is that it can be studied with real mathematical rigor, not merely described in words, and this sets it apart from vaguer proposals. When Ashtekar, Pawlowski, and Singh built their detailed models in the mid-2000s, they were able to follow a simplified universe through the bounce step by step, watching the equations remain finite and well-behaved at every moment, including the instant of maximum density that classical physics could not survive. The contracting phase, the bounce, and the expanding phase all emerged from a single, continuous calculation, with no infinity anywhere. This does not prove that our universe actually bounced, because the models are simplified, and loop quantum gravity itself is unconfirmed. But it demonstrated something valuable, that a bounce is not just a hopeful metaphor. It can be a concrete, calculable solution, a genuine alternative to the singularity that mathematics can trace all the way through. A natural question is whether a bouncing universe could go on forever, bouncing endlessly, and here the models grow cautious and interesting at once. Some versions allow for many cycles, a universe expanding and contracting again and again, though the changing entropy from cycle to cycle raises difficult questions about whether such a series could truly be eternal into the past. Others describe a single bounce, one contraction and one expansion, with a genuine before but not an infinite regress of them. Which of these is correct, if any, depends on details we do not yet know, and it connects directly to the puzzle of the arrow of time we will reach later in this list, because a universe that bounces has to explain how order and disorder carry across the bounce, a question that turns out to be surprisingly deep. A bounce, then, means the beginning was a passage rather than a birth. It means something was here before us, that it ended so that we could begin, and perhaps that our own distant ending might someday be another universe's dawn. But if a universe can bounce, some physicists have asked, might it also collide? Might our Big Bang have been not a rebound but an impact, the moment two worlds touched across a hidden dimension of space? That startling idea is the next entry on our list. Part 8. The Cyclic and Ekpyrotic Universe. The next model asks you to picture our entire universe as a sheet. Not a sphere floating in emptiness, but a vast, thin membrane. A surface with 3 dimensions of space, suspended in a space that has one more dimension than we can see. In this picture, everything we know, every galaxy, and every atom, is painted onto that membrane, that sheet, and we can no more perceive the extra dimension it hangs in than a drawing on a page can perceive the thickness of the book. This is the world of the Ekpyrotic model, and the cyclic universe built from it. And in it, our Big Bang was not a bounce and not a birth. It was a collision. The membrane on which our universe lives has a technical name. Physicists call it a brane, a word clipped from membrane, borrowed from string theory, the ambitious framework that tries to build all of physics from tiny vibrating strings. String theory requires more dimensions than the familiar 3 of space and 1 of time. Extra dimensions that are ordinarily hidden from us. The Ekpyrotic model takes this seriously and proposes that our brane is not alone. A second brane, a parallel universe sheet, hangs nearby in the extra dimension, close in that hidden direction, though we could never point to it. And these 2 branes are not fixed. They drift. Slowly, across an immense span of time, the parallel brane approaches ours, and eventually the 2 of them meet. When they collide, the energy released by the impact is colossal, and it floods both branes with heat and matter and radiation. On our brane, that sudden flood of energy is exactly what we have always called the Big Bang, the hot, dense fireball from which the familiar universe unfolded. The Big Bang, in this model, was not the start of our sheet's existence. Our brane was already there, drifting quietly through the extra dimension. The bang was the moment it was struck. The word for the model captures this fiery vision. Ekpyrotic comes from an ancient Greek term meaning out of fire, drawn from the Stoic philosophers who imagined a cosmos periodically consumed and reborn in flame. The name is old, but the physics is thoroughly modern. Picture the approach. In the strange quiet before the impact, 2 vast sheets of reality, each one an entire universe, drift toward each other across a gap you cannot see, in a direction you have never moved. On our sheet, everything is cold and nearly empty, smoothed out by an immensely long, slow contraction, waiting. There is no sound, because sound needs a medium, and the gap between the branes is more fundamental than any medium. The other brane draws nearer, not as a light in the sky, not as an object growing larger, but as a presence, approaching along a dimension perpendicular to everything you know. And then they touch. Not at one point, but everywhere at once, the two sheets meeting across their whole extent in the same instant. The energy of the contact ignites along the entire brane simultaneously, and space that was cold and dark and quiet floods with heat in every direction at the same moment. This is the Big Bang, felt from within, not an explosion outward from a center, but a fire lit everywhere at once, the aftermath of a collision between worlds. The Ekpyrotic model did not arrive as an idle picture. It was proposed as a direct, serious competitor to inflation, and this is the key to understanding why it was taken up. Inflation, for all its success, relies on a hypothetical field that no one has ever detected, and it predicts the untestable multiverse we met a few parts ago, features that trouble some physicists deeply. The Ekpyrotic model aims to explain the same observations that inflation explains: the flatness of the universe, its smoothness, the seeds of cosmic structure, but by a completely different route. Instead of a burst of exponential expansion stretching everything smooth, it uses a long, slow period of contraction on the brane before the collision. That slow contraction, its authors argue, can do the smoothing and flattening that inflation does, without the need for a burst of exponential growth at all. And in this picture, what came before the Big Bang was that long, quiet approach, the branes drifting together across the hidden dimension over an almost unimaginable span of time. Then the model goes further, into the cyclic version, and this is where it earns its most haunting implications. If two branes can collide once, why only once? In the cyclic model, the branes collide, and the impact drives them apart again. They separate, drift away from each other, and then, over an enormous stretch of time, the force between them draws them slowly back together until they collide once more, igniting another Big Bang, beginning another cosmic era. And then it happens again, and again. An endless series of collisions, each one a Big Bang, each one starting a fresh universe on the same eternal branes. The period between collisions can be extraordinarily long, potentially trillions of years, so that each Big Bang is separated from the next by spans that dwarf the current age of the universe many times over. Our 13.8 billion years is a brief chapter in a story with no discernible first page. The people behind this idea give it real weight. The Ekpyrotic scenario was introduced in 2001 by Justin Curry, Bert Overoot, Paul Steinhardt, and Neil Turok. Steinhardt and Turok then extended it into a full cyclic model in 2002 and laid it out for a general audience in their 2007 book, Endless Universe, Beyond the Big Bang. What made the proposal especially striking was the identity of one of its authors. Paul Steinhardt had been one of the founders of inflation, one of the physicists who repaired Guth's original idea and made it work. And here he was, years later, proposing a rival that did away with inflation's defining burst of expansion entirely. It was as if one of the architects of a great building had drawn up plans for a different structure on the same ground, unconvinced by his own earlier work. That kind of turn, from a serious scientist, is worth respecting. It signals genuine and honest disagreement about which story the evidence really tells. The model is not without heavy costs, and honesty requires naming them. Its entire foundation, the branes and the extra dimension, rests on string theory. And string theory remains unconfirmed. No brane has ever been observed. The extra dimension has never been detected. And there is an ongoing technical dispute about whether the Ekpyrotic mechanism can reproduce the detailed pattern of the oldest light as precisely as inflation does, a dispute in which each side cites different features of the data. The cyclic universe is a beautiful and serious idea, but it is built from ingredients we have not yet been able to reach out and touch. The idea of extra dimensions is so central to this model that it is worth pausing to make it less abstract, because it is easier to accept than it sounds. Imagine a tightrope walker on a wire seen from far away. To the walker, the wire offers one direction, forward or back, and the world seems one-dimensional. But to a tiny ant on that same wire, there is a second direction, around the wire's circumference, a whole dimension that was invisible from a distance because it is small and curled up. String theory proposes that our universe has extra dimensions exactly like that ant's circular direction, real but curled so small that we, seeing from far away in our everyday scale, never notice them. The Ekpyrotic model asks us to imagine one such extra dimension that is not curled small but stretched out, a hidden direction across which our universe membrane can face another. We cannot look along that direction, any more than the distant tightrope walker can see the ant's path, but it may be as real as any dimension we move through daily. The contrast between the Ekpyrotic model and inflation runs deeper than mechanism, and it reflects a genuine divide in taste and judgment among physicists. Inflation solves the puzzles of the early universe with a burst of violent expansion at the very beginning, stretching everything smooth in an instant. The Ekpyrotic model solves the same puzzles with the opposite motion, a long, slow, gentle contraction before the collision, patiently smoothing the universe over an immense span of time rather than in a sudden flash. Both can, in principle, produce a flat and uniform cosmos seeded with the fluctuations that become galaxies. They are like two different explanations for how a room came to be tidy, one proposing a whirlwind that somehow left order in its wake, the other proposing a long, careful, unhurried cleaning. Deciding between them requires looking closely at the fine details of the oldest light, and that is precisely where the ongoing dispute lives, with each side pointing to features of the data it believes favors its own picture. There is a particular prediction where the two models genuinely part ways, and it connects to the finale of this whole list. Inflation, with its violent early expansion, should generate a specific pattern of primordial gravitational waves, ripples in spacetime from the first instant. The Ekpyrotic model, with its slow and gentle contraction, generates almost none of these waves, because it lacks the violent stretching that produces them. This means the two ideas make opposite bets about something we might one day measure. If a strong signal of primordial gravitational waves is ever found in the oldest light, it would favor inflation and strain the Ekpyrotic picture. If no such signal is ever found, despite ever more sensitive searches, the Ekpyrotic model gains ground. For once, two rival stories about the beginning point toward a single observation that could help decide between them, a rare and precious thing in this subject. Still, the vision it offers is unlike any other on this list. It is a strange comfort and a strange dread braided together. There is comfort in the thought that the universe has done this before and will do it again, that a Big Bang is a recurring event rather than a lonely miracle, that beginnings are natural and repeatable. And there is dread in the same thought, the recognition that our beginning was somebody's ending, that the fire which made us was the aftermath of a collision, and that nothing, not even a universe, is ever truly the first of its kind. One thinker took this cyclic vision and pushed it to its most audacious extreme, proposing that the cold, dead, infinitely distant future of one universe is, precisely and mathematically, the hot beginning of the next. That astonishing idea is where we go now. Part 9. Conformal Cyclic Cosmology. We come now to what may be the most audacious idea in this entire catalogue, proposed by a man who has already appeared twice in our story. Roger Penrose, who proved the singularity theorems that gave the Big Bang its beginning, and who won a Nobel Prize for that work, spent his later years arguing that the beginning was not a beginning at all, but the smooth continuation of a previous universe's end. His model is called Conformal Cyclic Cosmology, and once you see how it works, it is very hard to forget, because it takes the bleakest imaginable future and turns it into a dawn. To follow Penrose's argument, we have to think about the far future of our own universe, the truly far future, almost inconceivably distant. Right now, the universe is full of structure, of stars and planets and galaxies, of matter clumped into shapes. But the universe is expanding, and that expansion is accelerating. And if it continues, the far future is a story of everything thinning out and fading away. The stars will burn out, new stars will stop forming, matter will decay over spans of time that make the current age of the universe look like an eye blink. And the black holes, those great engines at the centers of galaxies, will slowly evaporate, giving off faint radiation over almost endless stretches of time until even they are gone. What remains, in the end, is a cold, dark, nearly empty universe, containing almost nothing but massless radiation. Light, with no matter left to illuminate, spread infinitely thin across an ever-growing void. Now comes the insight that makes Penrose's model the strange and beautiful pivot on which everything turns. He asks a deceptively simple question. In that far future, with only massless radiation left, is there anything in the universe that can measure size or measure time? To have a clock, you need something with mass. To have a ruler, you need something with mass. Massless radiation, pure light, travels always at the same speed and, in a deep sense, does not experience time at all. Penrose argues that a universe containing only massless radiation has lost the very ability to define scale. There is nothing left in it that can say how big it is or how much time has passed, because everything that could have told you, everything with mass, is gone. And if nothing in the universe can distinguish large from small, then, Penrose argues, the distinction stops being physically meaningful. Follow that thought to its conclusion, because it is the whole model. If the cold, vast, infinitely dilute far future has no way to define scale, then mathematically it becomes indistinguishable from something very small and very hot and very dense, a state exactly like the beginning of a new Big Bang. Enormous and cold, with no ruler to measure the enormity, becomes identical to tiny and hot, with no ruler to measure the tininess. The end of one universe, smoothed of all scale, connects seamlessly to the fiery start of the next. Penrose calls each such universe an aeon, and he proposes that reality is an endless sequence of them, each beginning with a Big Bang and ending in the cold fade, with the end of every aeon flowing smoothly into the birth of the one that follows. In this picture, what came before our Big Bang was the unimaginably distant, cold, dead future of a previous universe, a universe so old that everything in it had faded to light. Drift, for a moment, in the last days of a previous eon. The sky is utterly black, because there are no stars, and have not been for longer than you could count. Space is colder than anything, emptier than anything, stretched so thin that the last particles are separated by gulfs that keep on growing. The final black hole, the last one in the entire universe, has just finished evaporating, giving up the last of its energy as a faint whisper of radiation, and now there is nothing left with any mass at all. Only light remains, spread across the infinite dark, going nowhere, marking no time. And in that absolute cold, that perfect scaleless silence, something quietly shifts. Without anything moving, without any violence, the vast emptiness ceases to be vast because there is nothing to measure it against. The endless cold becomes, in the same motionless instant, an unimaginable heat. The infinite thinness becomes an infinite density. The dead end becomes a beginning, and a new universe, a new eon, ignites out of the silence. Not because anything happened, but because scale itself had dissolved. What lifts conformal cyclic cosmology above pure poetry is that Penrose proposed a way to test it, an actual prediction about something we could look for in the sky. Here is the reasoning. In the previous eon, there were supermassive black holes, and over the long ages they evaporated, each one releasing an entire black hole's worth of energy. Penrose argued that this released energy, carried across the boundary from one aeon into the next, should show up in our universe as faint, circular marks in the oldest light, rings of very slightly altered temperature, each one the fossil of a supermassive black hole that had evaporated in the universe before ours. He named these marks Hawking points, after Stephen Hawking, whose work on black hole evaporation underlies the whole idea. If they were there, they would be nothing less than the signatures of a previous universe, written across our sky. In 2018, Penrose, working with Daniel Ahn, Christoph Meissner, and Pavel Nurovsky, published a paper claiming to have found them. The paper was titled, plainly, Apparent Evidence for Hawking Points in the Cosmic Microwave Background Sky. They reported points in the data where the energy appeared concentrated in just the way the model predicted, marks that they interpreted as the ghosts of evaporated black holes from the aeon before. For a moment, the possibility hung in the air that someone had detected a fingerprint from before the beginning, a physical trace of a universe that had ended so ours could start. But this is a video committed to the honest state of the evidence, and honesty requires the rest of the story. The claim was met with intense scrutiny, as extraordinary claims should be. Independent analyses, beginning in 2020, argued that the supposedly anomalous points were consistent with ordinary chance once you properly accounted for how many places in the sky had been searched. This is a well-known statistical trap, sometimes called the look elsewhere effect. If you scan a vast sky looking for unusual spots, you will find some unusual spots by sheer luck, the same way that scanning enough random noise will eventually turn up a pattern that looks meaningful but is not. More recent reanalyses of the same data, using careful statistical models, have reported no significant signal at all. As things stand today, the evidence for Hawking points is not accepted by the broader community. Conformal cyclic cosmology remains a fascinating minority proposal, argued for by one of the great physicists of the age, but it has not been established, and its central prediction has, so far, not survived independent testing. The model asks for other things too, which its own author openly acknowledges. For the scheme to work, mass itself must eventually fade entirely from the universe. Even the lightest particles that carry mass, like electrons, must, over cosmic eternity, somehow lose that mass or disappear, so that only massless radiation is left to erase the sense of scale. This is a speculative requirement, and Penrose does not hide it. It is one of the reasons the model sits at the edge of accepted physics rather than the center. And the aeons themselves are almost beyond imagining in length, long enough for the largest black holes to fully evaporate, a process that for the most massive of them takes something like 10 to the 100th power years, a span next to which the entire 13.8 billion year history of our universe is not even a rounding error. The word conformal in the name of Penrose's model carries the whole idea, and it is worth unpacking gently. A conformal transformation is a mathematical operation that stretches or shrinks distances while preserving angles and the local shape of things. Picture a map of the world, where the true sizes of countries are distorted, but the shapes and the angles of coastlines are kept faithful. Penrose's insight is that the laws governing massless radiation, pure light, are conformal, meaning they care about angles and shapes, but not about overall scale. Light does not carry a ruler, and so A universe with nothing but light in it is a universe in which stretching or shrinking everything makes no physical difference whatsoever. The cold, enormous end of one eon and the hot, tiny start of the next differ only in scale, and scale is exactly the thing that massless radiation cannot register. That is the mathematical bridge across which one universe becomes the next, a bridge that exists only because, in the end, there is nothing left with mass to notice the crossing. It is worth being fair to why Penrose pursued this idea, because it was not idle speculation, but an attempt to solve a real and serious problem, the very problem of the arrow of time we will reach shortly. Penrose was deeply troubled by the extraordinary low entropy, the astonishing order of our universe's beginning. Conformal cyclic cosmology was, in part, his attempt to explain where that order came from, by arguing that the smooth, ordered start of each aeon is inherited naturally from the smoothed-out, radiation-only end of the previous one. The heat death of one universe, in his scheme, is precisely the low entropy dawn of the next, because the process of everything decaying to light irons the universe flat and featureless in just the way a new beginning requires. Whether or not the model is correct, it was aimed at one of the deepest puzzles in cosmology, not invented for its own strangeness. That is the mark of a serious idea, even a contested one. The saga of the Hawking points also carries a lesson that reaches beyond this one model, and it is a lesson in scientific honesty worth stating plainly. When Penrose and his colleagues announced their claimed detection, they were making exactly the kind of bold, testable prediction that good science demands, staking a beautiful theory on a specific mark that should either be there or not. That the mark did not survive independent scrutiny is not an embarrassment, but the system working as it should. Other researchers took the claim seriously enough to test it rigorously, found that the apparent signal could be explained by chance and by the sheer number of places searched and reported so openly. The idea remains on the table, championed by one of the great physicists of the age, precisely because it was framed in a way that keeps it answerable to evidence. A theory that can be tested and has so far failed the test is in far better scientific standing than a theory too vague to be tested at all. Whatever its ultimate fate, conformal cyclic cosmology stands as one of the most remarkable answers ever given to the fear of an ending. It is a Nobel laureate's mathematical argument that the universe's cold, final, silent death is not a full stop but a doorway, that the very heat death we dread is indistinguishable from a new dawn, and that nothing, not even the end of everything, is ever really the end. Penrose thought he had found the marks of a previous universe written in our sky. The weight of evidence now says he probably had not, but the attempt itself raises the question that hangs over every single model in this video, the question we have been circling for hours and can no longer avoid. Could any of this ever truly be seen? We will return to that question at the end. First, string theory has two more strange beginnings to offer, and they suggest the universe may have no birthday at all. Part 10. String gas and the pre-Big Bang universe. String theory has already given us the colliding branes of the Ekpyrotic model, but it has more than one story to tell about the beginning. Two others deserve a place on this list, because they attack the singularity from completely different directions, and because between them they raise a possibility we have only touched on so far. Perhaps the universe has no birthday at all. Perhaps it stretches back forever, or lingered for an eternity in a strange, hot stillness before the Big Bang ever happened. These are the string gas scenario and the pre-Big Bang scenario, and they are stranger than they first sound. Begin with string gas cosmology, and with the single fact about strings that makes it work. In string theory, the fundamental objects are not points, but tiny vibrating strings. and strings have a property that point particles do not. There is a limit to how hot you can make them. If you pour energy into ordinary particles, they simply move faster, and the temperature rises without bound. But if you pour energy into a gas of strings, something different happens once you reach a certain critical temperature. The extra energy does not raise the temperature any further. Instead, it goes into making the strings longer, and into creating more of them, into stretching and multiplying rather than heating. There is a maximum temperature, called the Hagedorn temperature, that a gas of strings simply cannot exceed. Add all the energy you like, and the strings absorb it by growing rather than getting hotter. This ceiling changes the beginning completely. In the standard picture, running the universe backward means ever-rising temperature climbing toward infinity at the singularity. But if the universe is a gas of strings, the temperature cannot climb past the Hagedorn limit. So instead of a moment of infinite density and infinite heat, the string gas model proposes that the universe began in a long-lived, hot, nearly static state, a gas of strings hovering near that maximum temperature, holding there rather than racing to infinity. The singularity is replaced by a hot, quasi-steady beginning, a universe that lingered near its temperature ceiling before beginning to expand into the cosmos we know. String gas cosmology was introduced by the physicists Robert Brandenberger and Qumran Vafa in 1989, and it came with an unexpected bonus, an attempt to answer a question most models never even ask. Why do we live in 3 dimensions of space? String theory allows for 9 or more spatial dimensions, most of them presumed to be curled up small and hidden. Brandenberger and Vafa argued that the special thermodynamics of strings in the hot, early gas might naturally single out exactly 3 dimensions to grow large while the rest stay tightly wound. The reasoning involves strings wrapping around dimensions and, in 3 large dimensions, but not more, being able to find each other and unwind, allowing those dimensions to expand. Whether or not it is correct, it was one of the earliest serious attempts to derive the very shape of our universe, its number of large dimensions, from string theory itself rather than simply assuming it. The second scenario runs in almost the opposite direction, and it is called the pre-Big Bang scenario. Instead of a hot, dense start, it proposes a cold one. It imagines that in the infinite past, the universe was nearly empty, cold, flat, and very slowly expanding, a quiet and unremarkable place stretching back forever in time. Then, driven by a field native to string theory called the dilaton, this quiet universe gradually began to accelerate. It grew more and more curved, denser and hotter, winding itself up over an immense span until it reached the fierce, hot, dense state that we call the Big Bang. In this picture, the Big Bang was not the beginning. It was a peak in the middle of the universe's history, the climax of an unimaginably long, slow approach from a cold and eternal past. The consequence is worth stating clearly, because it is one of the most radical on this list. In the pre-Big Bang scenario, the universe is past eternal. It reaches infinitely far back in time. There is no first moment, no beginning to explain, because there was always a universe, quietly expanding in the cold, long before the Big Bang lit it up. The question, when did the universe begin, dissolves into the answer, it always was. The Big Bang becomes a dramatic event in an eternal history, rather than the opening line of the story. This scenario was developed by Gabriele Veneziano, one of the founding figures of string theory, together with Maurizio Gasparini, beginning in the early 1990s. And it offered a version of eternity that used only ingredients string theory already contained. Both of these scenarios share the deep uncertainty of everything built on string theory. String theory is a beautiful and powerful mathematical framework, but it has never been confirmed by experiment, and every prediction these models make inherits that enormous question mark. Neither scenario has yet been shown to match the precise measurements of the oldest light as successfully as inflation does, and inflation remains the benchmark against which all rivals are measured. These are serious ideas from serious physicists, but they are proposals, not established facts, and they are honest about it. What they add to our collection is a particular and unsettling thought, one that runs against the grain of how most people instinctively picture the cosmos. We tend to assume the universe must have had a beginning, a first moment, a cosmic birthday. It feels almost like a requirement. But these string scenarios suggest it may not be so. The universe might stretch back forever, or it might have lingered for an eternity in a strange hot stillness near the temperature ceiling of strings, with the Big Bang as a transition rather than an origin. And if that is true, then our craving for a first moment, our insistence that there must have been a beginning, may say more about the shape of human minds than about the shape of the cosmos. We are creatures who are born and who die, who experience everything as having a start, and we may simply be projecting that expectation onto a universe that never needed one. The Hagedorn temperature, the ceiling that string gas cosmology depends on, is a real and calculable feature of string theory, rather than a convenient invention. And its origin is genuinely elegant. When you heat any collection of objects, you are pumping energy into their motion. For point particles, that energy simply makes them move faster, and the temperature climbs without limit. But a string can absorb energy in another way. It can vibrate more intensely, and it can grow longer, and above a certain temperature, it becomes overwhelmingly favorable for the strings to soak up added energy by lengthening and multiplying rather than by speeding up. Because temperature is really a measure of energy of motion, and the extra energy is going into length instead, the temperature stops rising. It saturates at the Hagedorn value. This is why a gas of strings can linger in a hot, dense, quasi-steady state instead of racing toward the infinite temperature of a singularity. The ceiling is not imposed from outside. It falls out of what a string is. The pre-Big Bang scenario deserves a closer look at its most radical claim, that the universe is infinitely old, because it overturns something most people assume without noticing. We tend to picture the Big Bang as time zero, the first moment, with nothing before it. But the pre-Big Bang picture places the Big Bang in the middle of an eternal story. Stretching infinitely far into the past is a universe that was cold, nearly empty, and almost perfectly flat, expanding so slowly as to be nearly static, a vast quiet that had always existed. Driven by the dilaton field, this quiet universe gradually gathered itself, curving and heating over an immense span, winding up toward the fierce state we call the Big Bang, which then relaxes into the expanding cosmos we inhabit. In this telling, there is no first moment to explain, no beginning at all, only an eternal past, slowly building toward a climax. It is a genuinely different shape for time, one in which the question, when did it start, has no answer, because the premise of the question, that there was a start, is simply false. Both of these string scenarios share a quiet philosophical payload that is easy to miss amid the technical detail. They suggest that the human insistence on a first moment may be a projection rather than a discovery. We are beings who are born and who die, who experience every story as having a beginning, and it is natural for us to demand that the universe have one too. But the cosmos is under no obligation to match the shape of our lives. It might stretch back forever. It might have hovered in a strange hot stillness for an eternity. These possibilities are not stranger than a universe that popped into being from nothing, only differently strange. And they remind us that the very framing of our question, what came before, already smuggles in an assumption that there was a before to find. Perhaps the deepest thing these models teach is humility about the question itself. String theory has one more beginning to offer, and it is the strangest yet, because it does not place our universe at the start of anything, or even alone. It places our entire universe inside another one, hidden behind the horizon of a black hole in a parent cosmos. That is where we turn next. Part 11. Black hole cosmology. The next idea inverts your entire picture of where you are. It proposes that our whole universe, everything we can see, every galaxy and every star, and all 13 billion years of history, exists inside the interior of a black hole that formed in a larger universe that we can call the parent. In this view, the Big Bang was not a birth from nothing, and not a bounce from a prior cosmos in the ordinary sense. It was the other side of a collapse. Matter falling into a black hole in one universe emerged on the inside, as the expanding Big Bang of a new universe sealed forever behind the black hole's horizon. When you look out at the cosmos, you may be looking at the inside of something that, from the outside, is one of the darkest objects in another sky. This sounds like fantasy, but it grows from a real and suggestive coincidence, one that has intrigued physicists for decades. Every mass has associated with it a particular size, called its Schwarzschild radius, the size to which you would have to compress it in order to turn it into a black hole. Compress the Earth to the size of a marble, and it becomes a black hole. Compress the Sun to a few kilometers across, and it becomes a black hole. Now do the calculation for the entire observable universe. Take all the mass we can see, and ask how large its Schwarzschild radius would be, the size at which all that mass would form a black hole. The answer comes out to something on the order of tens of billions of light-years, which is remarkably close to the actual size of the observable universe. In other words, on the largest scale, our universe has roughly the mass-to-size relationship of a black hole. We appear to live inside a region whose contents, if you stood outside them, would look very much like a black hole from the exterior. That coincidence alone does not prove anything, and it might be nothing more than a curiosity of how the numbers are defined. But it inspired physicists to ask whether it could be taken literally. The idea that the universe could sit inside a black hole traces back to work by the physicist Roger Penrose in 1972, and others who noticed the same striking relationship. For a long time it remained a suggestive thought without a mechanism, a coincidence in search of a physics. The obvious problem was the singularity again. If matter falls into a black hole and collapses to a point of infinite density, then there is no room inside for a whole expanding universe. Something has to stop the collapse and turn it around. That mechanism was supplied more recently by the physicist Nikodem Poplawski around 2010. Poplawski used a version of gravity that includes an ingredient Einstein's standard theory leaves out, a property of space-time called torsion, a kind of twisting of the fabric of space that is sourced by the intrinsic spin of matter. In most situations, torsion is far too weak to matter, but at the extreme densities inside a collapsing black hole, Poplawski showed it can become important, and it can act as a powerful repulsion. Instead of crushing to an infinite point, the infalling matter reaches enormous but finite density, and then rebounds, bouncing outward into a new, expanding region of space, a baby universe, growing on the inside of the black hole, hidden behind its horizon and utterly inaccessible to the parent cosmos that made it. The collapse from the outside becomes an expansion, a Big Bang, on the inside. Sit with the symmetry of that, because it is the heart of the idea. A black hole and a Big Bang become the same event, seen from opposite sides. From the outside, in the parent universe, you see matter collapsing inward, vanishing behind a horizon, forming a black hole. From the inside, that very same event is a Big Bang, an outburst of space and matter expanding into a new universe. Which one you call it depends only on where you are standing. And if this is how universes are made, then the process could be endlessly fertile. Our own universe contains an enormous number of black holes, hundreds of billions in our galaxy alone, and every one of them, if the idea is right, could contain a baby universe of its own, each one a cosmos we can never observe, sealed away behind its horizon. Our universe would be a parent to countless others, even as it is the child of one. There is a related and even bolder idea that grows from this same soil, and it belongs to the physicist Lee Smolin. In 1992, and then in his 1997 book, The Life of the Cosmos, Smolin proposed what he called cosmological natural selection. Start with the notion that universes give birth to new universes through black holes. Now add one more ingredient, that each new universe inherits laws of physics that are slightly randomly varied from its parents, the way a child inherits slightly varied genes. Then something remarkable follows, an application of Darwin's logic to the cosmos itself. Universes whose laws happen to be good at making black holes will produce many offspring, and those offspring, sharing similar laws, will also be good at making black holes, and so on. Over many generations of universes, the population comes to be dominated by universes finely suited to producing black holes. Not because anyone designed them that way, but by simple selection, the cosmic equivalent of evolution. What makes Smolin's idea especially interesting is that, unlike most multiverse proposals, it makes a genuine prediction that could in principle be tested and proven wrong. If universes are selected for their ability to make black holes, then the laws of physics in our universe should be nearly optimal for black hole production. If someone could show that a small change to the constants of nature would produce many more black holes than we actually see, that would count as evidence against the theory. This is a rare and valuable feature. Most ideas about other universes seem forever beyond testing, but Smolin deliberately built his to be vulnerable to evidence, which is exactly what a scientific idea should be. Like every model on this list, black hole cosmology carries deep uncertainties. We do not know whether the Schwarzschild coincidence is meaningful or merely an artifact of how the quantities are defined. We do not know whether space-time torsion or any known mechanism really produces a habitable universe on the far side of a collapse, and it is not clear how such a claim could ever be checked from within, since the horizon that seals off a baby universe seals off all information as well. These are ideas at the frontier, honest attempts to explain a suggestive coincidence, not established descriptions of reality. The Schwarzschild coincidence that inspires black hole cosmology deserves a careful and honest examination, because it is both striking and slippery. It is true that if you take the mass of the observable universe and calculate the size at which that mass would form a black hole, you get a figure remarkably close to the actual size of the observable universe. On its face, this seems to be shouting something, but there is a subtlety that keeps physicists cautious. As the universe expands and we can see farther, the amount of mass within our horizon grows, and the relationship between that mass and that size shifts in ways that partly reflect how the quantities are defined, rather than a deep physical fact. Some physicists regard the coincidence as a genuine clue that our universe has the character of a black hole interior. Others regard it as an artifact, a near inevitability of the definitions that carries no real information. The disagreement is honest, and it is exactly the kind of ambiguity that makes this a frontier idea rather than an established result. A suggestive number is a starting point for investigation, not a conclusion. Poplavsky's mechanism, the torsion that turns collapse into a new, expanding universe, connects to a beautiful and often overlooked chapter in Einstein's own legacy. The standard theory of gravity that Einstein gave us describes how matter curves spacetime, but it leaves out any effect from the intrinsic spin of matter, the tiny rotation that fundamental particles carry. An extension of the theory, developed in part by Einstein himself alongside the mathematician Cartan, includes that spin, and it predicts that spinning matter gives spacetime a slight twist, the property called torsion. Under everyday conditions, this twist is far too feeble to detect, utterly negligible. But at the crushing densities inside a collapsing black hole, where matter is packed beyond all ordinary limits, the twist could grow strong enough to resist the collapse and reverse it, driving the bounce that births a new universe. It is a striking thought that a nearly forgotten refinement of Einstein's theory, an effect too small to matter anywhere we normally look, might be the very thing that turns a dying star's collapse into a cosmic beginning. Smolin's cosmological natural selection is worth defending as a model of what a good speculative idea should look like, whatever its ultimate fate. Most proposals about other universes are criticized, fairly, for being untestable, for describing realms we can never reach or measure. Smolin deliberately built his idea to avoid that trap. By proposing that our universe's laws should be nearly optimal for producing black holes, he gave critics a clear target. If someone could demonstrate that a modest change to the constants of nature would yield significantly more black holes than we observe, the theory would be in serious trouble. This willingness to be proven wrong is the opposite of the vagueness that dogs so many multiverse ideas. Whether or not cosmological natural selection turns out to be correct, and most physicists remain skeptical, it stands as an example of how even the wildest cosmological speculation can be disciplined into a genuinely scientific shape, answerable to evidence and honest about what would refute it. But the vision they offer changes how you might look at the sky. If we live inside a black hole, then every collapse we watch in the distant universe, every star that falls in on itself, every giant black hole at the center of a galaxy, might be a birth we cannot see, a new universe opening on the far side of a horizon. The darkest objects in the cosmos, the ones that swallow light and let nothing escape, could be the wombs of worlds. And if universes really can be born this way, in enormous numbers, each with its own slightly different laws, then we are led straight to a question that has haunted physics for 2 decades. Out of all the possible sets of laws a universe could have, why does ours have the particular ones it does? That question opens onto perhaps the most controversial idea in all of modern physics. And it is where we go next. Part 12. The string theory landscape. String theory set out to be the ultimate simplifier, the single framework that would explain all the forces and all the particles from one elegant principle, tiny vibrating strings. The hope was that it would predict a unique universe, ours, with its particular list of particles and its particular strengths of forces, all following inevitably from the mathematics. What string theorists found instead, to their considerable discomfort, was almost the opposite. The theory does not seem to pick out one universe. It appears to allow an almost unimaginable number of them, each with different physical laws, and this vast space of possibilities has a name. It is called the landscape, and it forces us to ask our question about the beginning in a new and humbling form. The reason the landscape exists comes back to the extra dimensions we met earlier. String theory requires more spatial dimensions than the 3 we experience, and the additional ones are thought to be curled up small, folded into intricate shapes too tiny to see. Here is the crucial point. There is not just one way to fold them. There are a staggering number of possible shapes, and each different way of curling up the extra dimensions produces a different effective universe, with different particle masses, different force strengths, and crucially, a different amount of energy woven into empty space. The theory does not tell you which folding nature chose. It offers a colossal menu of possibilities. and our universe corresponds to just one item on that menu, one particular way the dimensions happen to be arranged. The size of that menu is difficult to convey because the number is so large it defeats intuition. The count of distinct possible universes in the landscape is often quoted as around 10 to the 500th power. To feel the scale of that, consider that the total number of atoms in the entire observable universe is estimated at around 10 to the 80th. The landscape is not slightly bigger than that. It is that number of possibilities multiplied by itself many times over. A 1 followed by roughly 500 zeros, a quantity so vast that the atoms in the cosmos are as nothing beside it. String theory, hoped to yield a single answer, instead seems to yield more possible universes than there are particles to build them from. Now combine the landscape with an idea from earlier in this video, and it comes alive as a physical picture. Recall eternal inflation, the endlessly inflating background that continually buds off bubble universes. Suppose each bubble, as it forms, can settle into a different corner of the landscape, a different folding of the dimensions, and a different set of laws. Then the landscape stops being a mere menu of mathematical possibilities and becomes a real, populated multiverse. Somewhere out in the eternally inflating sea, bubbles are forming with every possible set of laws, an endless variety of universes, most of them nothing like ours. And in this combined picture, what came before our Big Bang was, once again, the inflating background, but now with an added twist. The reason our laws are what they are is simply that we happen to inhabit a bubble whose particular folding of the dimensions permits atoms and stars and eventually observers. That last move, explaining the properties of our universe by noting that we could only exist in a universe with the right properties, is called anthropic reasoning, and it is the source of enormous controversy. But it has one striking success to its name, and it is worth telling because it is one of the few times reasoning about a multiverse produced a number that was later measured. In 1987, well before the landscape had a name, the physicist Steven Weinberg considered the energy of empty space, what we now call dark energy. Theory predicted it should be enormous, but the universe plainly was not being torn apart, so it had to be small. Weinberg reasoned that in a multiverse with many different values, galaxies, and therefore observers, could only form in the rare universes where this energy was small enough not to prevent structure from clumping together. He predicted that we should find ourselves in such a universe with a small but non-zero dark energy. In 1998, the accelerating expansion of the universe was discovered, revealing dark energy at a value small, but not zero, roughly in the range Weinberg's argument had suggested. A prediction from anthropic reasoning had, unnervingly, come close to being right. The mismatch Weinberg was grappling with is itself one of the worst in all of physics, and it sharpens why the landscape is tempting. The strength of dark energy that we observe is smaller than the naive theoretical prediction by a factor of about 10 to the 120th. That is not a small discrepancy to be explained away by a minor correction. It is one of the largest mismatches between theory and observation ever recorded. The landscape offers a way out. In a multiverse spanning every value, the vast majority of universes have dark energy so strong that nothing can ever form in them, and only in the exceedingly rare universes where it happens to be tiny can galaxies, and us, come into being. We measure a strange, tiny value, not because a law demands it, but because we could not exist to measure anything else. The landscape emerged into prominence in the early 2000s, as string theorists confronted the discovery that their theory did not select a unique universe. The physicist Leonard Susskind gave the idea its name and made the case for it in his 2005 book, The Cosmic Landscape, and the reaction split the field, in a divide that persists today. To some physicists, the landscape is string theory's greatest embarrassment, a sign that the theory has lost its way. because a theory that can accommodate almost any universe predicts, in the end, no particular universe at all, and a theory that predicts everything predicts nothing. To others, the landscape represents a profound and necessary shift in what we should expect from physics. The recognition that some features of our universe may not be deducible from first principles at all, but are simply the local conditions in one bubble of an immense multiverse, the cosmic equivalent of the weather where we happen to live. This is a genuinely unsettling possibility, and it is worth feeling the weight of it. For centuries, the goal of physics was to show that the constants of nature, the masses of the particles, the strengths of the forces, were fixed by deep principles, that they could not have been otherwise, that a sufficiently clever mind could derive them from pure reason. The landscape suggests that this dream may be impossible for some of those constants, that they may have no explanation beyond that is the value in our bubble, a fact as arbitrary and as local as a street address. The deepest facts about our existence might not be woven into the fabric of necessity. They might just be where we happen to be. To understand why the landscape is so large, it helps to picture the extra dimensions as a shape that can be folded in a staggering number of ways, each fold trapping a different amount of energy. Imagine a complicated origami figure with hundreds of creases, where each crease can be set to one of several positions. The number of possible final figures explodes as you add creases, multiplying and multiplying until it dwarfs any number you can name. The extra dimensions of string theory are like that origami, with a great many independent ways to fold, twist, and thread them, and each distinct folding produces a universe with its own particular laws. The figure of 10 to the 500th is an estimate of how many stable foldings there might be. It is not a number anyone counted directly. It is what you get when you tally the ways the dimensions can settle, and the sheer combinatorial vastness of the possibilities is what turns a single theory into an ocean of universes. The anthropic reasoning that accompanies the landscape provokes such strong reactions that it is worth laying out both sides fairly, because thoughtful physicists genuinely disagree. To its critics, explaining a feature of our universe by saying observers could only exist where that feature holds is not an explanation at all, but a surrender, a way of giving up on the search for a deeper reason. They point out that this style of argument can excuse almost anything, and that it marks the moment physics stops doing its real job of deriving the world from principle. To its defenders, anthropic reasoning is simply honest bookkeeping about selection effects, no different in kind from noting that we find ourselves on a planet with liquid water because life could not have arisen on a barren one. If there truly is a multiverse with many values of the constants, then of course we measure life-friendly values, because only life-friendly regions contain anyone to measure anything. The disagreement is not really about logic. It is about whether the multiverse that would make the reasoning valid actually exists, and that is a question the landscape cannot yet answer. Weinberg's successful prediction of dark energy hangs over this whole debate like a challenge that will not go away. Here was a case where a physicist used exactly this multiverse and selection reasoning to forecast a specific, measurable quantity before it was measured, and the measurement, when it came, landed close to his estimate. To those sympathetic to the landscape, this is a genuine, if unsettling, success, a sign that anthropic reasoning can produce real predictions rather than mere excuses. To skeptics, it is a single striking coincidence that does not redeem an approach they consider fundamentally unscientific. Both sides acknowledge the prediction happened. What they cannot agree on is what it means, and that unresolved disagreement sits at the very center of one of the deepest arguments in physics today about whether the deepest features of our universe have explanations at all, or are simply the local conditions of the bubble we happen to inhabit. Whether the landscape is real physics or a symptom that string theory has drifted out of contact with testability remains fiercely disputed, and it may not be resolved for a long time. But it, along with every other model we have surveyed, runs eventually into a single deep puzzle, one that underlies all of them, and that we have so far only glanced at. It is the strangest feature of the universe of all, the one thing that makes the very idea of a before feel real. Time runs only one way, and understanding why turns out to be inseparable from understanding the beginning itself. That is where we go now. Part 13. The Arrow of Time. Every model we have explored eventually collides with the strangest fact about our universe, a fact so familiar that we almost never notice how bizarre it is. Time runs only one way. We remember the past, but not the future. A cup falls from a table and shatters, but shattered pieces never leap up and reassemble themselves into a cup. Heat flows from hot things to cold things, never the reverse on its own. Milk, stirred into coffee, spreads out and never gathers back together. This one-way character of time is so woven into experience that it feels like a background condition of reality itself. But when you look for its source in the laws of physics, you find something deeply puzzling, and the trail leads straight back to the beginning of the universe. Here is the puzzle. The fundamental laws of physics, at the microscopic level, do not care about the direction of time. Run a film of two particles colliding forward or backward, and both versions obey the same laws equally well. The equations work the same in both directions, and yet the world we live in is emphatically not like that. It has a clear, relentless arrow, pointing from past to future. Where does that arrow come from if the underlying laws are indifferent to it? The answer that physics has settled on lies in a single powerful principle, the second law of thermodynamics, which says that entropy, the measure of disorder, always increases. Order decays into disorder. Things fall apart, and the arrow of time is, at bottom, the direction in which entropy grows. But this only pushes the mystery back to a deeper and more startling place. If entropy has been increasing steadily for 13.8 billion years, then it must have been lower yesterday than today, and lower still the day before, and lower the further back you go. Follow that chain all the way to the beginning, and you reach an inescapable conclusion. The universe must have started in a state of extraordinarily low entropy, a state of astonishing order. Physicists call this the past hypothesis, the requirement that the early universe was fantastically, almost impossibly ordered. And that is the puzzle in its sharpest form, because a low entropy state is, by its very nature, overwhelmingly unlikely. Disorder is common and easy. Order is rare and special. A universe thrown together at random should have started in disorder. Ours did not. Something made the beginning special, and no theory fully explains why. The improbability is difficult to overstate, and one of the physicists we have already met put a number on it. Roger Penrose estimated the odds against our universe's low entropy beginning arising by chance, and the figure he arrived at is beyond anything the human mind can hold. He calculated it as 1 part in 10 to the 10 to the 123rd. That is not 10 to the 123rd, which would already be enormous. It is 10 raised to that entire staggering power, a number with so many zeros that you could not write them all down even if you used every particle in the observable universe as ink. Our ordered beginning was that special, that finely arranged, that far from what random chance would produce. The precision of the beginning is arguably the single most extreme fine-tuning in all of physics. There is a subtlety here that makes the low entropy of the early universe easy to misread, and it is worth getting right because it hides the fingerprint of the mystery in plain sight. When you look at the oldest light, the young universe appears almost perfectly smooth and uniform, the same temperature in every direction, Smoothness usually looks like disorder, like a gas spread evenly through a room. But when gravity is the dominant force, the situation reverses. Gravity wants to clump matter together, to pull it into stars and galaxies and black holes. So for a universe ruled by gravity, a smooth, evenly spread state is actually a state of very low entropy, a highly ordered and improbable arrangement, precisely because gravity is straining to break it up. The featureless smoothness we see in the oldest light is not the signature of disorder. It is the fingerprint of that improbable early order, the low entropy beginning showing itself as uniformity. Pause here, because this is the quiet, staggering heart of the whole question. Everything you value about being a conscious creature depends on this improbable beginning. Memory exists because the past has lower entropy than the future, because there is a fixed, ordered history behind us to remember. The sense that one thing follows another, that there is a story to your life with a beginning and a middle, that causes come before effects. All of it rests on the arrow of time, and the arrow of time rests on that near impossible low entropy start. If the universe had begun in the disordered state that chance overwhelmingly favors, there would be no arrow, no memory, no history, no story, no you. The simple fact that you have a past, that this moment follows the last one, that you can remember your own life, is not a given. It is a gift so improbable that the number describing its unlikelihood cannot be written down. Existence did not have to come with an arrow of time. Ours did, and everything we are is built on that one rare grace. The statistical understanding of entropy goes back to the physicist Ludwig Boltzmann in the 1870s, who defined it in terms of the number of microscopic arrangements that look the same from the outside. Boltzmann himself was troubled by exactly the question we are asking. Why is the universe not simply, in its most probable state, maximum disorder, a featureless soup? He floated a bold guess that perhaps the universe as a whole is in that disordered state, and we happen to live in a rare region that has randomly fluctuated into order, a temporary pocket of low entropy in an eternal, mostly dead cosmos. But this idea is now regarded as a dead end, and the reason it fails is instructive. If ordered regions arise from random fluctuations, then small ordered regions are vastly more likely than large ones. A single ordered brane, flickering into existence complete with false memories, would be enormously more probable than an entire ordered universe. So Boltzmann's guess predicts that you are almost certainly a lone brane hallucinating a world, which is absurd, and its absurdity is taken as proof that the low entropy of our universe cannot be a mere fluctuation. This unsettling scenario is known as the Boltzmann brane problem, and any theory that makes such lone branes common is considered to have refuted itself. So, if the ordered beginning was not a fluctuation, what was it? One of the most striking modern attempts to answer came in 2004 from the physicists Sean Carroll and Jennifer Chen, and it brings our question full circle. They proposed that the low entropy beginning was not a beginning at all, but a special middle. In their model, a quiet, high-entropy universe, empty and dead, can spontaneously spawn a baby universe, a new region that buds off and inflates, and that baby universe is ours. The key move is that time, in their picture, runs in opposite directions on either side of that budding event. On both sides, entropy increases away from the shared moment of lowest entropy in the middle. So there was a before, but its arrow of time pointed the other way. There are, in this model, people in the previous half of time, if we can call it previous, for whom our past is their future. Two arrows of time pointing away from a single shared moment, back to back. That image is a fitting place to end this part, because it shows how completely the question of the beginning and the question of time are entangled. You cannot ask what came before without an arrow of time to give the word before its meaning. And the arrow of time itself traces back to the improbable order of the beginning. We still do not know why the universe began in such a low entropy state. It is arguably the single deepest unsolved problem in all of cosmology, the one that underlies every other model we have discussed. Whether the arrow of time is fundamental or emergent, and whether a before with a reversed arrow is a real possibility or a mathematical curiosity, remains open. The distinction between the microscopic laws, not caring about time's direction, and the world plainly caring about it, is subtle enough that it repays a concrete example. Picture a short film of two billiard balls colliding and bouncing apart on a table. Run that film backward, and it still looks perfectly natural. Two balls approaching, colliding, and separating, obeying the same laws either way. You could not tell which direction was the true one. Now picture a film of a rack of billiard balls being broken, the tight triangle scattering across the table. Run that backward, and it looks absurd. 15 balls rolling in from all over the table and assembling themselves into a perfect triangle. The individual collisions in the break are each reversible, yet the whole event is not. The difference is entirely a matter of order and disorder, of how many arrangements look the same. The break goes from one special ordered arrangement to countless disordered ones, and never the reverse. And that is the arrow of time in miniature, built entirely from statistics rather than from any one-way law. There is a way to feel just how special the smooth early universe was, and it turns on the strange behavior of gravity. In almost any everyday situation, a smooth, evenly spread arrangement is the high entropy, disordered one, the state a system relaxes into. Perfume released in a room spreads until it is uniform, and that uniformity is disorder. But gravity reverses this logic completely. Because gravity pulls matter together, a smooth spread of matter under gravity is actually a highly ordered, low-entropy, unstable arrangement, straining to collapse into clumps. Left alone, gravity turns smoothness into structure, into stars and galaxies, and eventually black holes. And black holes are the highest entropy objects known. So the near-perfect smoothness of the early universe, visible as the evenness of the oldest light, is not the bland disorder it resembles. It is a fingerprint of astonishing, improbable order, the low entropy beginning wearing the disguise of a featureless glow. Reading that disguise correctly was one of the quiet triumphs of 20th century physics. The Carroll and Chen proposal of two-headed time deserves one more look because it is the point where our whole journey nearly closes into a loop. Their idea confronts the low entropy beginning not by explaining why a beginning was so ordered, but by denying that it was a beginning at all. If time can run in both directions, away from a single central moment of lowest entropy, then what we call the start of our universe is really the middle of a larger structure, with another universe, another arrow, unfolding on the far side. In that picture, there genuinely was a before, populated by events and perhaps by observers, but its time ran opposite to ours, so that its future is our past, and our past is its future. It is a dizzying thought, and it shows how completely the question of the beginning and the question of time's direction are woven together. You cannot fully answer one without the other, and after more than a century of work, we have answered neither. That honest incompleteness is exactly what carries us into the final part of this list. We have now walked through 13 serious attempts to describe or dissolve what came before the Big Bang: singularities and Planck walls, inflation and its endless bubbles, creation from nothing, time with no boundary, bounces and collisions and aeons, universes inside black holes and lost in a landscape of possibilities. The strange, precious arrow of time. And after all of it, one question remains. the one that decides whether any of this is science or only beautiful speculation. Could any of these ideas ever actually be tested? Is there any fossil, anywhere, from before or at the very start of the beginning, that we could still find and read? That is the finale, and it is where everything we have built now comes to rest. Part 14. The Fossils. We arrive at the final entry, and it is the one that decides the fate of all the others. For 3 hours we have walked through the most beautiful ideas physics has ever produced about the beginning. Ideas from Hawking and Penrose, from Guth and Lindy and Vilenkin, from Steinhardt and Turok and Smolin. Every one of them is a story about something we cannot see directly. And so the deepest question is not which story is right. The deepest question is whether any of them can ever be tested at all. Is there a fossil, somewhere, from before or at the very start of the beginning, that we could still find and read? Everything comes down to that. To answer it, we have to understand the oldest thing anyone has ever seen. It is called the cosmic microwave background, and it is light, the most ancient light in existence. It was released about 380,000 years after the Big Bang. At the moment, the universe had finally cooled enough for atoms to form. Before that moment, the universe was so hot that atoms could not hold together, and light could not travel freely, because it was constantly scattering off the dense fog of charged particles that filled all of space. The early universe was opaque, glowing but impenetrable, like the inside of the sun. Then, at 380,000 years, it cooled enough for electrons and nuclei to join into neutral atoms. The fog cleared, and light streamed out across the newly transparent cosmos. That light has been traveling ever since, stretched by the expansion of the universe from a fierce glow into faint microwaves, and it fills the entire sky today at a temperature of just 2.725 degrees above absolute zero. It is the cooled afterglow of the primordial fire, and we have mapped it in exquisite detail. But here is the hard truth about that ancient light, and it brings back an image from the very beginning of this video. Earlier we spoke of walls, the Singularity, and the Planck epoch, the places where our theories give out. The cosmic microwave background is a wall too, but a different kind. It is not a wall where theory fails. It is a wall where vision fails. We cannot see any light from before that moment, 380,000 years in, because before it, the universe was opaque, and no light escaped to carry us an image. It is the earliest snapshot we will ever have by ordinary light, a curtain drawn across the first 380,000 years. And everything that happened before it, all the inflation and bouncing and colliding we have discussed, lies hidden behind that curtain. Any fossil from that earlier time cannot be seen directly. It can only be read indirectly, as a faint imprint pressed onto this oldest light. And there is one imprint above all others that physicists dream of finding, because it would be a direct fingerprint of the first instant. Recall that inflation, if it happened, was a period of violent expansion in the very first fraction of a second. Such a violent stretching of space would inevitably have generated ripples in space-time itself, gravitational waves, primordial ones, waves in the fabric of the cosmos, born in the first moment of its existence. And these primordial gravitational waves would have left a very specific, very subtle mark on the oldest light, a particular swirling pattern in the way that light is polarized, a twist that physicists call B-mode polarization. If we could detect that swirl, it would be as close to a photograph of the beginning as we could ever hope to obtain. Direct evidence of inflation, a fossil from the first fraction of the first second. It is one of the great prizes in all of science. The hunt for that swirl produced one of the most instructive dramas in the history of modern cosmology, and it is worth telling in full, because it captures both the hope and the heartbreak of trying to read a fossil from the beginning. It is March of 2014. At a telescope called BICEP 2, stationed at the South Pole where the air is thin and dry and the sky is clearest, a team of scientists believes it has done the impossible. They have found the swirl. They have detected the primordial pattern, the fingerprint of inflation itself, written in the oldest light. They call a press conference. The news breaks across the world. One of the physicists, whose theory is being confirmed, is filmed on his doorstep, receiving the news in person, his eyes filling with tears. Champagne is poured. For a few weeks, it is hailed as one of the greatest discoveries in the history of science. A direct glimpse of the birth of the universe. And the phones of Nobel committees are already, surely, being lifted. And then, over the following months, the doubt creeps in. Another team, working with the Planck satellite, studies the dust in our own galaxy, the ordinary dust between the stars, and shows that this dust can produce a swirl that mimics the primordial one. And the patch of sky that BICEP 2 had chosen turns out to hold far more of that dust than anyone had assumed. Slowly, painfully, the discovery dissolves. The swirl was most likely not the fingerprint of creation. It was the dust of our own galaxy, lying between us and the beginning. They had reached for the first instant and touched only the dust nearby. That episode is not a story of failure so much as a story of how brutally hard this is and of how honestly science, at its best, corrects itself. The search did not stop. The BICEP and Keck experiments continued, combining their data with the Planck satellites, and they have steadily tightened the limits without yet finding the signal. The strength of the sought-after imprint is captured by a single number, called the tensor-to-scalar ratio, and the measurements now push it below about 0.032. The signal, if it exists, is fainter than that, hiding somewhere below the current reach of our instruments. But a new generation is coming. In the high desert of Chile, an array called the Simons Observatory is beginning its work. A larger project, called CMB, Stage 4, is being planned. And a satellite led from Japan, called Lightbird, is being built specifically to hunt this inflationary signal from space, designed to push the sensitivity down to a tensor-to-scalar ratio of around 0.001, a tenfold improvement. Within the coming decade or so, these instruments could either detect the fingerprint of inflation at last, or push the limits so low that the simplest versions of inflation are ruled out. Either result would be historic, and the other models we discussed have their own hoped-for fossils, most of which have so far come up empty. Penrose's Hawking points, the rings from a previous aeon, were searched for and, as we saw, have not survived independent testing. Strange features in the oldest light, like an unusually large cold region, sometimes called the cold spot, were at one time floated as a possible bruise from a collision with another universe. But no such interpretation has been confirmed. The bouncing and cyclic and colliding models each predict subtle differences in the pattern of the primordial fluctuations, and cosmologists are working to see whether the data could ever tell them apart. So far, inflation remains the model that fits best, the benchmark all the others are measured against. But the question is genuinely open, and it is being pursued with real instruments and real data right now. Here is the honest, sobering possibility we must face at the end. Some versions of inflation predict a signal so faint that it may be forever below any conceivable detection. If nature chose one of those versions, then the true story of the beginning could be correct and permanently unprovable, a fossil that exists but can never be dug up. We may already have a photograph of the fingerprint of creation buried in the same oldest light we have mapped so carefully and simply lack, and perhaps always lack, the resolution to see it. That is a strange and humbling thought, that the answer might be sitting in our data, present but unreadable, forever just beyond the edge of what our instruments can resolve. And so, after 3 hours and 14 ideas, we arrive not at an answer, but at a question, and there is a quiet dignity in that. Think of what it means to stand at this edge. Human beings, on a small planet, around an ordinary star, have looked back 13.8 billion years, mapped the oldest light in the sky to a precision of millionths of a degree, and worked out more than a dozen mathematically serious accounts of what might lie beyond the first wall, and then had the honesty to say, of all of them, we do not yet know. We are listening for a whisper from before the beginning, a signal so faint it may never come, building ever more sensitive instruments in deserts and at the poles and in space, straining to hear it. There is something almost unbearably moving in a science that can say, after all of that effort, we do not know, but here is exactly how we are trying to find out. That honesty is not a weakness of the search. It is the finest thing about it. Remember how we began. A beginning, we said at the start, is the one thing physics is worst at explaining. After everything we have walked through, that is still true, but it is true now in a richer way. The beginning resists us not because we lack imagination. We have 14 serious answers from the greatest minds of the age. It resists us because it may sit forever just past the last wall on the far side of the oldest light, in a place our vision cannot reach. And perhaps the question itself, as Hawking suggested, quietly loses its meaning there. The way south loses its meaning at the pole. Yet we keep asking. We keep building the instruments and running the numbers and listening in the cold and the dark for a signal from before all signals. Because that, in the end, is what it is to be the kind of creature that wonders. To stand at the edge of the knowable and ask, gently, what came before, knowing we may never hear an answer, and asking all the same. It is worth understanding why gravitational waves, of all things, are the fossil physicists most want to find, because the reason cuts to the heart of the whole problem. Ordinary light cannot reach us from before the moment the universe became transparent, 380,000 years in. That curtain is absolute for light. But gravitational waves, ripples in the fabric of space-time itself, do not scatter off the primordial fog the way light does. They pass through everything, almost untouched, from the earliest instants. A gravitational wave born in the first fraction of a second would have been traveling ever since, carrying information from a time no light can show us. This is why they are the true prize. They are the one messenger that could, in principle, cross the wall of the oldest light and bring us word from the first moment directly. The catch is that primordial gravitational waves are expected to be almost unimaginably faint, their imprint on the oldest light a whisper beneath a whisper, which is why detecting them has defeated every attempt so far. The measurements that have been achieved, even without finding the prize, are staggering feats of human ingenuity, and they deserve their due. To detect the swirl imprinted by primordial gravitational waves, experiments must measure the polarization of the oldest light, the direction in which those ancient microwaves vibrate, and separate a signal that might amount to a few parts in 100 million from everything else in the sky. They must do this while filtering out the glow of our own galaxy's dust, the interference of our atmosphere, and the faint contamination of nearer cosmic structures bending the light along its journey. That the BICEP and Keck and Planck teams have pushed the limits as far as they have, ruling out ever fainter signals, mapping the oldest light to millionths of a degree, is among the most delicate measurements ever performed by our species. Even the failures, like the retracted announcement of 2014, are failures at a level of precision that would have seemed impossible a generation earlier. There is a deeper reflection buried in this final entry about what it means for a question to be answerable at all. Throughout this list, we have met ideas of extraordinary beauty, and the temptation is to ask simply which one is true. But the finale, reframes that temptation. A model that makes no difference we could ever detect, that predicts nothing distinguishable from its rivals, sits in a strange category, neither proven nor disproven, perhaps forever. Much of the real work in cosmology now is not dreaming up new stories about the beginning, of which there are already many, but hunting for any observable consequence that could separate them. Any fossil, any faint asymmetry, any whisper in the oldest light. The value of a beautiful idea, in the end, depends on whether the universe left us a way to check it, and whether the beginning left any such trace at all remains the open question on which the entire subject turns. So let the question rest now, unanswered and beautiful. The universe may have begun in a burst from nothing, or bounced from a world before, or collided into being, or simply always been. We do not know, and tonight we do not need to. It is enough to have stood at the edge together and looked out into the dark before the dawn of everything. Let that vast, quiet mystery settle over you like a blanket of stars. Sleep well, and good night.